Hello and welcome to Sleepy Science. Tonight, we are stepping into something you have lived inside every second of your life, yet may never have truly understood. Time itself. You feel it moving. You watch it change your body, and you organize your entire existence around clocks. But what if time is not flowing at all? What if your future already exists? Your present is only a construction of the brain, and every star above you is showing you a universe that has already passed. Across 100 strange, calming, and deeply thought-provoking questions, we will explore how gravity bends time, why fear can stretch a few seconds, how dreams make minutes feel like hours, whether the past could ever be reached, and what time might mean when the final stars and black holes have disappeared. Before we begin, tell me in the comments where you are listening from and what time it is there. And don't forget to like the video and subscribe for more calm, mind-opening science. Now, allow the clocks around you to grow quiet. Let the day slowly fade away, and let us begin our journey into the deepest mystery of time. Why time may not actually be flowing. You feel time carrying you forward, but physics has never detected anything that literally flows from the future through the present and into the past. A clock does not measure a moving substance called time. It counts regular physical changes, such as the vibration of atoms, the swing of a pendulum, or the rotation of Earth. This raises a subtle possibility. Perhaps events change, but time itself does not travel anywhere. The sensation of passage may instead be created by the structure of consciousness. Your brain preserves traces of earlier experiences, receives new information, and predicts what may happen next. By placing these states in sequence, it produces the powerful feeling of movement through a continuous present. A melody works in a similar way. No individual note contains the motion of the music. Progression appears because your mind remembers the previous notes while hearing the next. Without memory, you might experience change without feeling a journey through it. Physics can describe how long processes take and how events are ordered without adding a universal mechanism that pushes reality forward. Even saying that time moves at 1 second per second explains nothing, because movement normally requires time in which to occur. If time were flowing, another kind of time would be needed to measure that flow, creating an endless chain. None of this proves that temporal passage is unreal, and scientists still debate how physical time relates to conscious experience. It does suggest, however, that the most familiar feature of time may not be a fundamental property of the universe. Stars burn, bodies age, and decisions produce consequences, but these changes may not be floating down an invisible river. The river you feel could be the mind's way of turning a sequence of changing states into a life that seems to move. The disturbing possibility that your future already exists. The person you will become decades from now may already occupy a place in reality, hidden from you not because that future is non-existent, but because you have not reached it. This possibility comes from an interpretation of relativity often called the block universe, in which every event belongs to a larger structure of space-time rather than appearing one moment at a time. The idea becomes scientifically interesting because relativity does not give the cosmos one universal present. Observers moving differently can disagree about which distant events are happening at the same time, and physics does not identify either viewpoint as the single correct one. If reality consisted only of one cosmic now, nature would need a universal method of deciding whose now was real, yet no such privileged clock has been found. The block universe view avoids this problem by treating past, present, and future as different locations within one complete history. Your childhood, this moment, and your final day could all belong to that structure, just as cities can exist along a road, even while you stand in only one of them. This does not necessarily mean that your choices are meaningless or controlled by an outside force. Your future decisions could exist precisely as decisions produced by your character, reasoning, fears, and desires. A choice can be part of reality while still occurring because you make it. The difficulty is that no observer can step outside space-time and inspect the entire pattern. so the idea remains an interpretation rather than a proven picture of existence. Other philosophers argue that only the present is real, or that the future gradually comes into being. What physics establishes more firmly is that the everyday belief in one universal present is difficult to defend. Your future may already exist, but it remains inaccessible, unpredictable, and emotionally open from where you stand. You still have to enter it without knowing what it contains. And perhaps that ignorance is what allows a fixed structure, if one exists, to feel like a life being freely discovered. Why you are always experiencing the past. Reality has already moved on before your mind finishes showing you what just happened. Every experience begins with information that requires time to travel. Light reflected from a face must cross the distance to your eyes. Sound must move through the air, and signals from your skin must travel along nerves before the brain can interpret them. Across a room, these delays are extremely small, but they are never zero. At greater distances, the effect becomes impossible to ignore. You see the moon as it was slightly more than a second ago, and the sun as it was roughly 8 minutes earlier. A star located 100 light years away appears as it was a century ago, because the light now entering your eyes began its journey long before the present night. Yet even after information reaches your body, conscious experience does not appear instantly. The brain must process color, motion, depth, sound, touch, and body position through different pathways that operate at different speeds. It then combines these uneven signals into one stable scene. Without this coordination, a person's moving lips and spoken words might feel disconnected, and your own movements could seem delayed or fragmented. To prevent that confusion, the nervous system gathers information across short intervals and predicts what is probably happening now. This is why perception is not a raw live broadcast, but an intelligently edited reconstruction of the immediate past. Illusions sometimes reveal the editing process by making movement appear in the wrong position or causing one sense to alter another. These effects do not mean that your senses are useless. They show how actively the brain builds a usable world from delayed evidence. The moment you call now is therefore a small window containing information from several recent instants, carefully synchronized so that life feels continuous. You never encounter the external world at exactly the moment it exists. You meet its light, vibrations, and signals shortly afterward, transformed into an experience so coherent that the past feels perfectly present. The strange reason time feels faster as you get older. A summer once seemed large enough to contain an entire lifetime, yet now whole seasons can disappear before you feel you have fully entered them. This does not mean time is physically accelerating as you age. A minute measured by a clock remains the same length. What changes is the way your brain pays attention to experience and stores it in memory. Childhood is filled with first encounters. The first day at school, the first long journey, the first time you understand a difficult idea, or the first place that feels entirely new. Novel experiences demand more attention because the brain cannot rely on familiar patterns. It records more details, creates more distinct memories, and divides a period into many recognizable events. When you later look back, that densely recorded period feels long because your memory contains many landmarks. Adult life often becomes more predictable. You wake at similar times, travel familiar routes, perform repeated tasks, and move through weeks built from nearly identical pieces. The brain becomes efficient by compressing routine information instead of preserving every repetition. This is useful for functioning, but it can leave months with surprisingly few memorable boundaries. In the moment, a busy day may feel slow because your attention is occupied, yet in retrospect, an entire year may seem short because little within it stands apart. Another explanation involves proportion. To a 5-year-old, 1 year represents a large fraction of all remembered life. To someone much older, the same year forms a smaller portion of their personal history. This comparison may influence how duration feels, although it is not a complete scientific law. Attention also matters. When you wait, monitor the clock, or feel uncomfortable, every interval becomes noticeable. When your mind is absorbed in familiar responsibilities, it may stop measuring experience so closely. The unsettling part is that your life may not feel shorter because fewer things are happening, but because fewer moments are being encoded as unique. This suggests a gentle way to resist the apparent acceleration, not by trying to slow clocks, but by giving the mind more events worth distinguishing. Learning unfamiliar skills, visiting new places, changing small routines, and paying deliberate attention can create richer memory. They cannot extend your biological lifespan, yet they may prevent long stretches from collapsing into a blur. Time does not necessarily speed up as you grow older. Your brain simply becomes better at recognizing the world, and in becoming efficient, it may stop noticing how much of that world is passing through you. What would happen if time suddenly stopped? The moment time stopped, nothing dramatic would appear to happen, because there would be no functioning observer left to witness it. Stories often imagine frozen raindrops, motionless people, and one character walking freely through a paused world. But that character would require time to think, move, breathe, and see. If time truly stopped everywhere, every physical process would stop with it. Atoms would no longer change state. Electrical signals would not travel through the brain. Hearts would not beat, and chemical reactions would not continue. Light would not cross the room to reach your eyes, so there would be no frozen scene available to inspect. Sight requires photons to move and neural tissue to process them. Movement through a stopped universe would therefore be impossible. Even the thought, "time has stopped," could not form, because one stage of thought must follow another. This reveals why a total halt of time is not like pressing pause on a video. A paused video exists inside a larger world, where the screen, viewer, and clock continue operating. For the entire universe to stop, there could be no external background in which the stoppage lasted. Asking how long time remained frozen would become meaningless, since duration itself would be absent. If everything stopped for what an outside observer might call 1 billion years and then resumed in exactly the same state, no one inside the universe would notice any interruption. There would be no aging, decay, memory, or evidence left behind, because all of those require change. From within reality, the stop and immediate restart would be indistinguishable from no stop at all. Physics does allow processes to occur at different rates. Motion and gravity can make clocks disagree, and matter can be cooled until many forms of activity become extremely slow. But slowing physical change is not the same as turning time off. Even near absolute zero, quantum systems do not become perfectly inert, and no known experiment has produced a region where time itself vanishes while surrounding observers continue normally. The idea of stopping time therefore exposes a hidden truth. Time cannot be separated cleanly from events. You know time through change, and you know change because one state differs from another. Remove every possible difference, and there is no clock, thought, or witness capable of declaring that a pause has occurred. A universe without passing events would not feel silent, dark, or peaceful. It would not feel like anything. It would contain no experience at all until change began again. Why you can remember the past, but not the future. Your memories all point in one direction, because the universe leaves records behind, not records ahead. A memory is not a mysterious window through which the mind looks backward. It is a physical change created when an event affects the brain. Neurons alter their connections, proteins are produced, and patterns of activity become easier to reactivate. In the same way, footprints record someone who has already crossed the ground. Tree rings preserve earlier seasons. Photographs contain light gathered during past events, and fossils carry traces of organisms that once lived. Each record exists because something happened and caused a later system to change. The future has not yet interacted with your brain in this ordinary causal sense, so it has left no neural trace for you to retrieve. Remembering tomorrow would require information about a later event to reach you before the processes that produce it, reversing the normal order of cause and effect. The laws governing many small physical interactions can work similarly in either temporal direction, which makes the asymmetry of memory especially interesting. The answer appears to emerge from the larger condition of the universe. The early cosmos began in an unusually ordered state, and since then, usable energy has spread out while physical systems have tended toward more probable, disordered arrangements. This allows events to create durable traces as they unfold. A glass falling can scatter fragments across the floor, produce sound, alter the air, and create memories in witnesses. Those later effects contain information about the intact glass, but scattered fragments do not normally organize themselves in advance as a record of a glass that will break tomorrow. The direction in which records accumulate gives conscious creatures access to what has happened, while leaving what comes next uncertain. Your brain also uses remembered patterns to predict the future, but prediction is not recollection. You may imagine tomorrow vividly, estimate what someone will say, or recognize that a familiar routine is likely to continue, yet these are models built from earlier experience. They can fail because the event has not yet produced the evidence that would make it a memory. This difference shapes your emotional world. The past feels fixed because it has already left consequences in your body and surroundings. The future feels open because many outcomes remain compatible with the information currently available. Perhaps a being in a radically different universe could possess records arranged in another direction, but no known organism remembers events that have not causally affected it. You face backward through memory and forward through expectation, standing between evidence and possibility. That division may seem limiting, yet it is also what makes learning possible. The past can instruct you precisely because it has marked you, while the future still waits to discover what you will do with those marks, how gravity can bend time itself. A clock placed closer to Earth does not experience time in exactly the same way as an identical clock placed higher above it. This strange difference comes from Einstein's discovery that gravity is not simply a force pulling objects through an unmoving background. Massive objects change the geometry of space-time around them, and time is part of that geometry. The deeper a clock sits within a gravitational field, the more slowly it runs when compared with a clock farther away. You would never notice this effect by watching an ordinary wristwatch because the difference across a room is incredibly small. But modern atomic clocks are precise enough to detect it even when separated by modest changes in height. Light also reveals the same effect. When light climbs away from a massive object, its frequency shifts slightly because the passage of time differs between the place where it began and the place where it is received. This gravitational redshift was measured in laboratory experiments on Earth and became one of the important confirmations of general relativity. The effect grows much stronger near extremely dense objects. Close to a neutron star, a distant observer would see processes occurring more slowly than similar processes far from the star. Near the boundary of a black hole, the difference can become so extreme that an infalling object appears to slow dramatically from the viewpoint of someone watching at a safe distance. Yet the falling observer's own clock would continue ticking normally from their local perspective. This is the important lesson. Gravity does not make time feel broken to the person living within it. Your heartbeat, thoughts, and watch always seem ordinary beside you. The difference appears only when clocks following different paths are brought together or compared by exchanging signals. Time is therefore not a single rhythm imposed equally on every part of the universe. It is shaped by location, mass, and the curvature surrounding each observer. The ground beneath you is not merely holding your body down. It is also placing you within a slightly different rate of time than someone standing far above. The difference is tiny, but it is real, which means gravity has been quietly bending every second of your life. Why astronauts return to Earth slightly younger? An astronaut can spend months above Earth and return, having aged a few thousandths of a second less than the people who remained below. The difference is far too small to see in a face or feel in a body, but it can be calculated and measured because orbital travel places astronauts between two competing effects. The first comes from speed. A spacecraft in low Earth orbit moves at roughly 28,000 kilometers per hour, circling the planet about once every 90 minutes. According to special relativity, a moving clock accumulates slightly less time than a clock traveling more slowly. This is not caused by mechanical damage or an inaccurate watch. Every process aboard the spacecraft is affected together, including chemical reactions, brain activity, and biological aging. To the astronaut, nothing feels slower because their thoughts and instruments share the same motion. The difference becomes visible only when their elapsed time is compared with clocks that followed another path. The second effect comes from gravity. Astronauts orbit higher above Earth's surface, where gravity is slightly weaker, and weaker gravity makes their clocks run a little faster relative to clocks on the ground. For crews aboard the International Space Station, however, the slowing caused by their high orbital speed is larger than the speeding caused by their greater altitude. The final result is that they return slightly younger than they would have been if they had remained on Earth. A stay of around 6 months can produce a difference of several milliseconds. Longer missions accumulate more, although still nowhere near the dramatic leaps shown in science fiction stories. Traveling much closer to the speed of light would make the effect far greater. A Voyager moving at an enormous fraction of light speed could experience only a few years, while many more years pass for people on Earth, allowing travel into Earth's future without reversing time. Present-day astronauts offer a modest but real demonstration of the same principle. They do not merely carry clocks through space. Their bodies are clocks, following paths through space-time that differ from yours. When they return, the missing milliseconds are invisible, yet they remain a physical reminder that aging is not governed by one universal rhythm. The amount of life you experience depends partly on how you move through the universe. The possibility that past, present, and future exist together. Your life may be less like a story being written line by line and more like a complete path laid across space-time, with consciousness encountering only one region of it at a time. In relativity, an object is not described merely by where it exists in space. It traces a world line, a continuous history containing every event associated with that object, from its earliest state to its latest. Your own world line includes your first breath, every place your body has occupied, this current experience, and whatever events eventually complete your life. Thinking this way does not automatically mean that all moments are occurring simultaneously, because simultaneity itself depends on the observer. Instead, it suggests that events separated into past, present, and future by human experience may all belong to the same space-time structure. A mountain does not need one slope to vanish when you stand on another. The summit, valley, and distant path can all be parts of one landscape, even though you occupy only a narrow location. Space-time may possess a similar kind of completeness. What you call the present would then be less like a universal wall sweeping across reality, and more like the local perspective from which you encounter your own path. This view helps explain why physics has difficulty identifying one cosmic now. Observers moving differently can arrange distant events into different sets of present moments without contradicting any experiment. The universe does not seem to provide a master clock that slices the whole cosmos into one officially existing instant. Some philosophers and physicists therefore argue that the division between past, present, and future may describe consciousness more accurately than it describes reality itself. Yet the idea must be handled carefully. It does not mean you can visit yesterday by simply changing your thoughts, receive information from tomorrow, or treat cause and consequence as meaningless. Events can coexist within a larger structure while remaining separated by limits on motion and communication. The pages of a closed book may all be present together, but a character inside the story still reaches them in order and cannot read ahead. Whether space-time is truly complete in this way remains an interpretive question, rather than a settled experimental fact. Other views hold that reality genuinely grows as new events occur. Still, the possibility changes how you think about disappearance. If every event retains a place within space-time, the moments you call lost may not have been erased from reality. They may simply lie elsewhere along a path your awareness can no longer revisit. The future, in the same quiet sense, may not be waiting in nothingness. It may be another region of the structure, unreachable until your life carries you there. Why fear can make a few seconds feel much longer. A moment of danger can stretch so dramatically that a few seconds seem large enough to contain an entire scene. During fear, your brain shifts away from ordinary observation and into survival mode. Stress hormones increase alertness, attention narrows toward possible threats, and details that would normally be ignored suddenly become important. The movement of a hand, the sound of approaching footsteps, the distance to an exit, or the expression on another person's face. Because so much information is being noticed and stored, the event can later feel as though it lasted far longer than it truly did. Scientists have tested whether frightening situations actually make the brain process the world in slow motion, and the evidence suggests something more subtle. People do not appear to gain a dramatically faster visual system during danger. Instead, the brain forms denser and more vivid memories. So when the event is recalled, it contains more mental landmarks than an ordinary moment of the same duration. A quiet 10 seconds may leave almost no trace, while 10 frightening seconds can produce a sequence of sharp images, sounds, and bodily sensations. Looking back, the crowded memory feels longer. Fear also forces attention into the present. You stop thinking about distant plans or unrelated concerns because survival demands immediate decisions, and every small change becomes meaningful. This is why waiting for an impact or hearing an unexplained noise in darkness can feel almost endless. The clock has not slowed, but your relationship with each second has changed. Fear reveals that experience duration is not determined by clocks alone. It is shaped by how much the brain notices, how strongly the body reacts, and how deeply an event is written into memory. A terrifying moment may be brief in the outside world, yet inside you it can expand into something that remains present for years. What happened before time began? The question, what came before the beginning of time, may be asking for a moment that could never have existed. According to the standard picture of modern cosmology, the early universe was once extraordinarily hot, dense, and rapidly expanding. When scientists run their equations backward, matter and radiation are compressed into increasingly extreme conditions until our present theories can no longer describe what happened reliably. This boundary is often associated with the beginning of the Big Bang, but the Big Bang was not an explosion occurring at one point inside an already existing emptiness. It was the early expansion of space itself, affecting every region of the observable universe. If time emerged together with that expanding universe, then asking what happened before it may resemble asking what lies north of the North Pole. The grammar of the question is familiar, but the direction it assumes may end at the boundary. Still, scientists do not know with certainty that time had an absolute beginning. General relativity becomes incomplete at the earliest conditions, where quantum effects should have been important, and a successful theory combining gravity with quantum physics has not yet been confirmed. Some proposed models suggest that the universe passed through an earlier contracting phase before expanding again. Others imagine repeating cosmic cycles, a quantum state without ordinary time, or a larger process in which our Big Bang was only one transition. These ideas are scientifically motivated, but none has yet received decisive observational support. Even the word before may lose its normal meaning in such models, because ordinary cause, duration, and sequence may behave differently under conditions far beyond anything we can reproduce. The honest answer is therefore not that there was definitely nothing before the Big Bang, nor that another universe certainly existed. It is that our tested descriptions reach a limit. The cosmic microwave background allows us to study the universe when it was hundreds of thousands of years old, and other evidence lets scientists infer much earlier stages. But the first fraction of cosmic history remains hidden behind incomplete physics. Perhaps time began there. Perhaps it changed form. Perhaps the beginning was not a first moment, but a boundary beyond which the word earlier no longer works. The question remains powerful because it leads you to the edge where language, intuition, and scientific knowledge all begin to lose their familiar shape. Why looking into space means looking back in time. A powerful telescope is not only an instrument for seeing farther away, it is a machine for uncovering earlier chapters of the universe. Light travels at an enormous but finite speed, so every distant object is observed as it was when the light began its journey. The farther away the source, the older the image reaching us. This allows astronomers to arrange the sky almost like a historical record. Nearby stars show relatively recent stages of stellar life, while galaxies billions of light years away appear as they existed when the universe was much younger. Telescopes such as Hubble and the James Webb Space Telescope detect light that has traveled for most of cosmic history, revealing galaxies before they developed the mature structures seen around us today. These ancient systems are often smaller, more irregular and actively forming stars, offering evidence of how galaxies grew through collisions, gas accumulation, and generations of stellar birth and death. Looking deeply into space also changes the kind of light astronomers must collect. As the universe expands, light traveling across it is stretched toward longer wavelengths. Radiation that began as visible or ultraviolet light can arrive as infrared, requiring instruments designed to detect wavelengths your eyes cannot see. This is why some telescopes observe from space, above much of Earth's atmosphere, where faint infrared signals can be measured more clearly. The images they produce are not simple snapshots of how the cosmos looks everywhere today. Different objects within the same image may belong to very different periods, depending on their distances. One galaxy may be shown from a time before Earth existed, while a nearby star appears from only decades or centuries ago. Astronomy therefore studies space and history at once. No telescope can show a distant galaxy in its current condition because its newest light has not yet arrived. That galaxy may have changed, merged with another, or stopped producing stars, but the universe has not delivered that information to us. The night sky is not a single present spread above your head. It is a layered archive, filled with messages released at different ages of the cosmos. Each deeper observation does more than increase distance. It moves the scientific view closer to the universe's youth, allowing you to watch creation not as a finished picture, but as a history still traveling toward your eyes. How fast would you need to travel to reach the future? You are already traveling into the future, but to arrive there dramatically faster than everyone else, you would need to move at a speed almost indistinguishable from that of light. Einstein's special relativity shows that motion changes how much time a traveler experiences. Any movement creates some time dilation, even when you walk across a room. But at ordinary speeds, the difference is far too small to notice. The effect becomes significant only when a spacecraft approaches light speed. At about 99.5% of light speed, roughly 10 years could pass on Earth while the traveler experiences only about 1 year, ignoring the periods of acceleration and slowing down. Move even closer to light speed, and the separation becomes much greater. A crew might cross enormous distances and return to find that generations have passed at home while their own bodies have aged far less. This is genuine travel into the future because the astronaut reaches a later era of Earth after experiencing less time personally. It does not require a portal, a wormhole, or a machine that reverses history. It follows directly from tested physics and has been confirmed on smaller scales with fast-moving particles and precise clocks. Yet there is a barrier no object with mass can cross. As a spacecraft accelerates, giving it additional speed becomes increasingly difficult, and reaching light speed would require an unattainable amount of energy. Collisions with even tiny particles would also become extremely dangerous at such velocities, while shielding, propulsion, and navigation would demand technologies far beyond what humanity currently possesses. So there is no exact speed at which future travel suddenly begins. Every journey carries you forward, and every sufficiently rapid journey makes your personal route through time shorter than the route followed by those who remain behind. The real threshold is practical rather than magical. To leap decades or centuries ahead while aging only a little, you must travel extraordinarily close to the universe's speed limit. The future is therefore not locked behind an impossible law, but behind an engineering challenge so immense that the physics allows the destination long before civilization knows how to reach it. Why time may disappear inside a black hole. Beyond a black hole's event horizon, time does not simply stop, but the familiar distinction between moving through space and moving toward the future begins to lose its ordinary meaning. Outside a black hole, you can choose many spatial directions while continuing inevitably forward in time. Inside the horizon, the geometry of space-time is altered so severely that traveling toward the center becomes as unavoidable as traveling toward tomorrow. You cannot remain still, turn around, or choose a path that leads back outside, because every future-directed route points deeper inward. This is sometimes described by saying that space and time exchange roles, although that phrase is only an approximation. What truly changes is the structure of possible paths. For someone falling through the horizon of a sufficiently large black hole, local time would continue normally. Their watch would tick, their heart would beat, and crossing the boundary might not produce a sudden visible sign. A distant observer, however, would receive increasingly delayed and weakened light from the falling person, making them appear to slow and fade near the horizon. The two descriptions are not contradictions. They arise because the observers follow radically different paths through curved space-time. The deeper mystery lies at the center, predicted by classical general relativity. There, the equations produce a singularity, a boundary at which curvature becomes extreme, and the theory can no longer provide a complete physical description. Asking what happens to time at that point may therefore be impossible with our current knowledge. Time might not literally vanish, rather, the concept may stop being usable in the form we understand. Most physicists expect that a future theory of quantum gravity will replace the classical singularity with a more complete explanation. But no experimentally confirmed theory yet tells us what that explanation is. Black holes do not prove that time ends inside them. They reveal something more unsettling. The categories you use to separate distance, direction, duration, and destiny may belong only to the gentler regions of the universe. Inside the horizon, the future is no longer an open landscape of destinations. It narrows toward a place where the language of clocks may finally reach the edge of what it can describe. The strange link between time and the expansion of the universe. The universe carries a kind of history within its changing size, allowing astronomers to use expansion as one of the largest clocks nature has ever provided. On the greatest scales, galaxies are not merely flying through empty space from a central explosion. The distances between widely separated regions increase as space itself expands. By measuring how rapidly this expansion is occurring today and reconstructing how matter, radiation, and other forms of energy influenced it in the past, cosmologists can estimate the age of the universe at about 13.8 billion years. This does not create a universal clock for every object, but within the large-scale cosmological model, there is a useful quantity called cosmic time. It represents the time measured by ideal observers moving with the average expansion rather than racing through space relative to it. Cosmic time allows scientists to describe stages such as the formation of the first atoms, the ignition of early stars, and the growth of galaxies within one shared historical framework. Expansion also changes the light traveling through the universe. As space stretches, the wavelengths of freely moving light are stretched with it, lowering their energy. The faint microwave radiation filling the cosmos was once far hotter, but expansion has cooled it over billions of years, turning it into a preserved signal from the young universe. In this sense, the changing cosmos carries evidence of its age in temperature, density, and the separation of galaxies. The relationship becomes even stranger because expansion is now accelerating. If this continues, extremely distant galaxies will eventually cross a cosmological horizon beyond which signals emitted in the future can never reach us. They will not necessarily vanish from existence. They will become causally inaccessible, as the intervening space grows too quickly for newly emitted light to overcome. Far future observers may see a darker and emptier sky, with much of cosmic history hidden beyond reach. Expansion therefore does more than alter distances. It determines which regions can exchange information, how ancient radiation evolves, and what future observers will be able to know about the past. The age of the universe is not marked by hands moving around a dial. It is written into the widening space between galaxies, the cooling light left from creation, and the gradual closing of doors across the cosmic horizon. Why some stars you see may have already died. A star can vanish from the universe and still continue shining in your sky for generations. The reason is not that its light survives mysteriously after death, but that the final message announcing its destruction may still be traveling toward Earth. Stars are separated from you by enormous distances, so every point of light is seen at an earlier stage of its history. Yet this does not mean that most visible stars are probably already dead. Many nearby stars are only tens or hundreds of light years away and can remain stable for millions or billions of years, making it extremely likely that they still exist. The possibility becomes more interesting with massive stars, which consume their nuclear fuel much faster than smaller ones. A star several times heavier than the Sun may live for only a few million years before its core collapses, while a small red dwarf can continue shining for trillions of years. Betelgeuse, the reddish star in Orion, is often described as a star that may already have exploded because it is nearing the final stage of its life and lies hundreds of light years away. In reality, astronomers cannot say that it has already died, and its remaining lifetime could still extend for tens of thousands of years or longer. If it exploded tonight from Earth's perspective, the physical explosion would actually have occurred centuries earlier, with the light only now completing its journey. The same principle applies across the galaxy. Telescopes do not reveal stars as they are at this instant, but as they were when their light departed. A supernova, therefore, does not merely show you the death of a star, it shows you an ancient event finally arriving. Somewhere in the darkness, a star may already have collapsed into a neutron star or black hole, while its former light continues crossing space unchanged, preserving the appearance of a sun that no longer exists. The sky can hold both presence and absence in the same point of light, reminding you that seeing something is not always proof that it is still there. How your memories create the feeling that time has passed. You do not feel the length of your past directly. You estimate it from the traces your mind managed to keep. Memory gives time its emotional distance by dividing experience into events, changes, and recognizable versions of yourself. When you think about yesterday, you do not retrieve every second in order. You reconstruct fragments: a conversation, a room, a mistake, a meal, the weather, or the feeling with which the day ended. The brain groups continuous experience into meaningful episodes, often placing boundaries where a goal changes, a new place is entered, or something unexpected occurs. These boundaries help explain why two periods of equal clock time can appear radically different in memory. A day containing several distinct experiences may seem long when recalled because it leaves many separate landmarks. A day spent repeating one familiar activity may later feel compressed into a single vague block, even if it felt slow while you were living through it. This creates an important difference between prospective time and retrospective time. While an event is happening, duration is influenced by attention. Watching the clock can make minutes drag. Afterward, duration is judged partly from how much information remains accessible. Rich memory can make a period expand in hindsight, while sparse memory allows it to collapse. Your sense that years have passed also depends on changes in identity. You compare the person you remember being with the person you are now, and the difference between them becomes a kind of internal distance. A childhood room feels far away, not because the memory contains a measurable amount of time, but because it belongs to a mind, body, and world that no longer fully match the present. Memory is imperfect, however. Each recollection is reconstructed from surviving details, and may be altered by later knowledge, emotion, and repeated retelling. This means the past you feel moving away is not a complete recording, but a changing model built in the present. Without memory, events could still occur, yet you might possess little sense of having traveled through them. Time would leave changes in your body and surroundings, but not the personal trail that tells you how far you have come. Your remembered life is therefore not the clock behind you. It is the collection of marks from which your mind infers that a journey has taken place. Why dreams can make minutes feel like hours. A dream can seem to contain a journey, an argument, and an entire unfolding story, even though the episode may have occupied only a short part of the night. This does not necessarily mean that the dreaming brain can fit hours of fully experienced time into a few real minutes. Experiments with lucid dreamers, who know they are dreaming and can communicate through planned eye movements, suggest that simple counting inside dreams often takes roughly as long as it does while awake. More complex actions can take somewhat longer, possibly because imagined movement lacks ordinary sensory feedback. The enormous duration you remember after waking is more likely created by the unusual way dreams construct scenes and memories. A dream does not need to simulate every step of a long journey. It can place you in a city, give you the immediate conviction that you have been traveling for days, and then move directly to another setting without representing the missing hours. Films use a similar shortcut. One scene can imply months of history without showing every day. While dreaming, the brain accepts these jumps because the systems responsible for critical evaluation and consistent reasoning are operating differently, especially during rapid eye movement sleep. Memory is also unstable. Dreams can blend recent experiences, older memories, emotions, and invented background information into one narrative. You may awaken with the impression that a long sequence occurred, even though only a few vivid moments were actually experienced. In addition, estimating duration requires reliable landmarks, and dreams often contain no clocks, routines, sunlight patterns, or stable causal order. Without those signals, the mind has little basis for measuring how much time has passed. Some dreams may unfold slowly, while others compress events or leap across unexplained intervals. But scientific evidence does not support the popular claim that every few seconds of sleep can contain years of continuous experience. What dreams reveal is something more subtle. The feeling of duration depends not only on how many minutes occur, but on how a story is assembled and remembered. A dream can give you the memory of a long life without making you consciously live every moment of it, showing how easily the mind can create the weight of time from only a handful of scenes. The mystery of why time moves in only one direction. Nothing in ordinary life allows you to step into yesterday, yet many of the equations describing nature do not strongly object when the direction of time is reversed. If you filmed 2 billiard balls colliding and played the recording backward, the reversed motion could still obey the basic laws of mechanics. The same is often true for the movements of planets, electromagnetic interactions, and many processes involving individual particles. The mathematics can describe one state leading to another without clearly labeling which frame belongs to the past. Yet the world around you possesses an unmistakable direction. Causes leave consequences. Photographs record earlier scenes. Wounds appear after injuries. And messages are received only after they are sent. A small asymmetry does exist in certain particle interactions involving the weak nuclear force, but it does not by itself explain why coffee cools, people age, or history cannot be replayed. The larger mystery may lie not in the local laws, but in the conditions from which the universe began. A set of rules can permit motion in either direction, while a particular starting arrangement forces almost every large process to develop one way. Imagine a hill whose shape allows a stone to move upward or downward, but the stone begins near the summit and is released. The rules do not forbid the reverse path, yet the initial position gives the motion a natural direction. In a similar sense, the universe appears to have begun in a remarkably special state, and everything that followed inherited an orientation from it. Your experience of earlier and later may therefore be connected to cosmic history rather than to a hidden command written into every particle. Time's direction feels absolute because every record, body, and machine around you was formed within the same unfolding universe. You cannot turn around and walk into the past, not necessarily because nature lacks reverse-compatible laws, but because the entire physical world, including the mind asking the question, is already traveling along the direction established by its beginning. Why broken things never reassemble themselves? A shattered glass does not leap from the floor, gather its fragments, absorb its scattered sound, and land perfectly restored on the table, although the motions of its atoms do not make such a reversal strictly forbidden. The true obstacle is probability. An intact glass is a highly specific arrangement. Countless atoms must occupy a narrow range of positions that produce one recognizable object. Once it falls, the same atoms can be distributed across the floor in an enormous number of different ways. The impact also transfers energy into vibrations, heat, air movement, and sound, spreading the event into the surrounding room. For the glass to rebuild itself naturally, every fragment would need to move in precisely the correct direction at the correct speed, while the dispersed energy returned from the walls, air, and floor in exactly the right pattern. A tiny deviation would cause the pieces to miss, rotate incorrectly, or collide in the wrong order. This is not logically impossible in the same way that a square circle is impossible. It is so overwhelmingly improbable that the age of the universe provides nowhere near enough opportunities for it to occur in an ordinary room. At microscopic scales, random motion can occasionally create brief increases in order, especially in very small systems. But large objects contain so many interacting particles that coordinated reversal becomes effectively unobservable. The broken state is not preferred because nature dislikes perfection. It is preferred because there are vastly more ways to be broken than to be whole. Human beings can reverse some damage by gathering pieces, applying energy, and following a plan. But even repair produces waste heat and alters the surroundings. The restored object never appears without a cost elsewhere. A broken cup therefore teaches something deeper than fragility. Order is not the default destination of matter. It is a rare arrangement that must be built, protected, and sometimes rebuilt by processes capable of selecting one possibility from an almost limitless field of disorder. How? Entropy creates the arrow of time. The direction of time becomes visible whenever concentrated energy spreads into forms that are harder to use. This tendency is described through entropy, a measure related to how many microscopic arrangements can produce the same large-scale condition. A warm object beside a cold one contains an imbalance. Energy is concentrated more strongly in one place than another. As they interact, energy disperses until their temperatures become similar. The reverse process, in which random molecular motion spontaneously gathers heat back into only one object, is extraordinarily unlikely because far fewer microscopic arrangements produce that uneven state. Entropy gives this statistical tendency a physical language. In an isolated system, it is overwhelmingly likely to increase or remain unchanged, and this growth supplies the thermodynamic arrow of time. You identify a melting ice cube as a later state because its organized crystal structure has become liquid and its coldness has been distributed into the surrounding drink. You know smoke has spread after a fire because its particles occupy a wider range of positions. Entropy does not mean that everything instantly becomes chaotic, nor does it prevent local order from forming. Stars, crystals, plants, and human brains can all develop complex structures by using energy and releasing greater disorder into their surroundings. A living cell maintains its organization by taking in concentrated energy and exporting heat and waste. Local order survives because the total process still increases entropy overall. The deepest puzzle is why the universe began with entropy low enough for this long transformation to occur. The early cosmos was hot and nearly uniform, yet gravity made that smooth condition exceptionally special, leaving enormous room for stars, galaxies, black holes, and life to develop while total entropy rose. Every usable energy difference around you is part of that unfinished cosmic descent toward equilibrium. Entropy does not push time like a motor, but it distinguishes the direction in which natural histories are overwhelmingly likely to unfold. The arrow you feel in cooling rooms, aging bodies, and fading stars may be the universe gradually exhausting the differences that allow change to leave a trace. Could time travel to the past ever be possible? The universe does not clearly forbid a road into yesterday, but every route we know seems guarded by conditions reality may never allow. Einstein's general theory of relativity describes gravity as the shape of space-time, and some mathematically valid solutions contain paths that curve so strongly that a traveler could return to an earlier event. Physicists call these closed time-like curves, routes that always feel locally forward to the traveler, yet eventually loop back toward their own past. Such paths appear in unusual models involving rapidly rotating universes, infinitely long rotating cylinders, or extreme gravitational geometries. The mathematics is serious, but mathematical permission is not the same as physical possibility. Many of these models require objects that do not exist in nature, impossible sizes, carefully arranged motion, or forms of matter with properties never confirmed. Even if space-time could be bent into a loop, maintaining that structure might demand enormous energy and expose it to destructive quantum effects. Some researchers suspect that nature contains a kind of chronology protection, an unknown mechanism that prevents usable routes into the past from forming, although this has not been proved. There is also a practical boundary hidden inside every proposed time machine. In many models, you could not travel to a date earlier than the creation of the machine or the formation of the loop. The device would act more like a doorway connecting two moments after its construction than a vehicle capable of visiting ancient history. No experiment has ever sent a person, object, or verified message into the past, and no observation currently shows that such travel occurs naturally. The honest scientific position is therefore neither a confident yes nor an absolute no. Relativity leaves narrow doors open in theory, while known physics places heavy barriers in front of them. Perhaps the past is permanently sealed. Perhaps it is reachable only under conditions the universe never produces. For now, yesterday remains close enough to remember, yet more inaccessible than the most distant galaxy. Why you cannot escape the present moment. No matter how carefully you search for the present, it disappears the instant you try to hold it. Human language treats now as though it were a sharp point separating what has happened from what has not. But lived experience requires a small span of duration. You cannot hear a single musical note as a melody, understand a spoken word from one frozen sound, or recognize movement from one motionless image. Consciousness must retain what has just occurred while receiving what follows, creating what psychologists sometimes call the specious present, a brief window in which several moments are experienced as one coherent whole. This window is why a sentence feels continuous rather than like isolated noises, and why a bird flying across the sky appears to move instead of repeatedly appearing at unrelated positions. You cannot step outside this experiential window because every attempt to observe it becomes another event within it. Thinking about the past happens now. Imagining the future happens now. Even the wish to escape the present is itself a present mental state. The past is available only through surviving records and recollection, while the future appears through expectation, planning, and prediction. Neither can become the location from which you are conscious. Your attention may wander into childhood or rehearse a conversation that has not occurred, but your body continues receiving sensations, regulating breath, and maintaining awareness in the current act of remembering or imagining. This does not mean there is one universal present shared by the entire cosmos. Physics makes such a cosmic now difficult to define. It means that for a conscious organism, experience always has a local center. You cannot live from nowhere, and you cannot experience an event before the processes creating that experience occur. The present may be impossible to isolate, yet it is equally impossible to leave. It is not a room imprisoning you, but the only opening through which memory, sensation, and possibility can enter awareness. Everything you have ever known has met you there, in a moment too narrow to keep and wide enough to contain a life. How boredom makes time feel almost endless. An empty minute can feel longer than a crowded hour, because boredom turns your attention toward time itself. When an activity offers little novelty, challenge, or emotional reward, the brain has fewer external events to process, so awareness begins monitoring the absence of change. You notice the clock, your posture, the silence, and the uncomfortable fact that nothing seems to be happening. Each check of the time becomes another marker, dividing a short interval into many consciously observed pieces. This creates a paradox. Boredom often leaves few memorable details afterward, yet it feels painfully slow while it is occurring. Psychologists distinguish these two forms of judgment. Prospective duration is estimated while you know you are waiting, and it tends to expand when attention is directed toward time. Retrospective duration is judged later from the number of events stored in memory, so the same uneventful period may shrink when recalled. A dull afternoon can therefore feel endless while you are trapped inside it, and almost disappear when you look back. Boredom is not simply a lack of entertainment. It often arises when you want to engage but cannot find an activity that feels meaningful, sufficiently challenging, or under your control. A task that is too easy may fail to hold attention, while one that feels pointless can produce the same restless emptiness, even if it requires effort. The brain begins searching for stimulation, and every unsuccessful search makes the interval more noticeable. This may be why waiting without information feels longer than waiting with clear progress. A moving line, a countdown, or a visible task gives the mind structure, while uncertainty leaves attention circling around duration. Boredom can be unpleasant, but it also carries information. It signals that your attention is available and searching for a better use. Sometimes that signal leads to creativity, exploration, or reflection. At other times it leads only to repeated clock checking. The seconds have not changed their length. What has changed is the number of times your mind turns around to watch them leave. Why the universe may have no universal clock. There may be no single clock anywhere in existence that can declare what time it is for the entire universe. On Earth, synchronized clocks create the comforting impression that every place shares one common present. But this agreement is something humans construct by exchanging signals and correcting for distance. Even two clocks placed far apart cannot be compared instantaneously, because information about one clock must travel to the other. The moment distance enters the problem. Deciding which events happened at the same time requires a method of synchronization, and different observers may not always divide events in the same way. Each object instead carries its own measure of elapsed time along its particular journey. A person resting on Earth, a spacecraft crossing the solar system, and a particle moving through a laboratory can accumulate different amounts of time between comparable events. Their local clocks are not pretending or malfunctioning. Each records the duration experienced along its own path. This personal measure is sometimes called proper time, and it is more fundamental in relativity than the idea of one master clock ticking beyond the stars. Cosmologists do use something called cosmic time when describing the history of the universe, but it should not be mistaken for an absolute metronome. Cosmic time is defined for ideal observers who move with the average large-scale expansion of the cosmos. It is extremely useful for saying that the universe is about 13.8 billion years old, or that certain structures formed during particular eras. Yet it depends on a carefully chosen reference frame, and works best only when the universe is smoothed out across enormous distances. Inside galaxies, near dense objects, or for travelers moving differently, local clocks still follow their own histories. There is another difficulty. The universe may extend far beyond the region we can observe, and some areas are separated from us so completely that no signal sent today will ever reach them. A universal clock would therefore need to coordinate regions that cannot communicate. Using a standard no observer could physically verify everywhere. Nature appears to provide relationships between clocks rather than one clock above them all. You can compare durations when paths meet again, exchange light signals, and calculate how different observers relate their measurements, but you cannot climb outside the universe and read its official time. The clocks in your home seem united because they occupy nearly the same environment and move almost together, not because they are receiving commands from a cosmic center. Beyond that familiar scale, time becomes local, relational, and dependent on the path through reality. The universe may have an age, a history, and measurable rhythms without possessing one universal second that belongs equally to everything. Perhaps there is no answer to the question, what time is it everywhere? Because everywhere has never been gathered into one shared now. What the end of time might actually look like. The end of time may arrive without an explosion, a final countdown, or any last observer noticing that the universe has reached its closing moment. In the most widely discussed far future scenario, time itself does not suddenly switch off. Instead, the physical differences that make change useful gradually disappear. Stars shine because matter contains concentrated sources of energy capable of producing light and heat. Planets remain active because temperatures, pressures, and chemical conditions are uneven. Life functions because energy flows from ordered sources into less useful forms. If cosmic expansion continues for an unimaginable length of time, galaxies beyond our local region will become unreachable. Star formation will eventually cease. Existing stars will burn out, and the universe will grow colder and darker. Matter may remain, but fewer organized processes will be available to mark meaningful change. This state is often called heat death, although the name can be misleading. It does not mean everything reaches a warm temperature. It means the universe approaches a condition in which energy has become so evenly dispersed that little useful work can be extracted from it. A clock requires a repeating process. An atom must oscillate, a planet must orbit, a pulse must recur, or some system must move reliably from one state to another. In a universe where organized structures have faded and interactions have become extremely rare, building or reading such a clock could become practically impossible. Time might still exist in the equations, and isolated quantum events might still occur, but there would be almost nothing present to count them, compare them, or remember them. This creates a strange distinction between the continuation of time and the disappearance of history. History requires durable records and meaningful differences between earlier and later states. If no observers remain, no new structures form, and nearly every region settles into featureless equilibrium, then an additional trillion years may add almost nothing recognizably new to the cosmos. Some theories predict even more extreme possibilities. If protons eventually decay, a process never yet observed, ordinary matter could slowly disappear. If the current accelerated expansion persists, empty space may dominate almost completely. Other models allow the properties of dark energy to change, potentially producing very different endings, so scientists cannot claim to know the universe's final state with certainty. The safest conclusion is that the end of time may not be a boundary at which reality announces that no more seconds are allowed. It may be an asymptotic fading, with events becoming rarer, distances becoming greater, and clocks becoming less meaningful, until the distinction between another age and no age at all matters to nothing that remains. The universe may never reach a final moment. It may simply continue into a silence so complete that time survives only as a possibility, with almost nothing left to happen inside it. Why your entire life is only a tiny moment in cosmic time. If the entire history of the universe were compressed into a single calendar year, an 80-year human life would occupy less than a fifth of a second before midnight on December 31st. The comparison is difficult to feel because your mind was built to measure breakfasts, winters, birthdays, and generations, not billions of years. The universe is about 13.8 billion years old, while a human lifetime may contain only several decades. Even the whole history of our species is extremely recent on this scale. Modern humans have existed for roughly 300,000 years, which would place our entire species within only the final minutes of the cosmic year. Recorded history would appear during the last few seconds. The first cities, empires, libraries, machines, and scientific instruments would all arrive almost at the end, after most of the imaginary year had already passed without anyone on Earth to remember it. The solar system itself formed only after the universe had existed for more than 9 billion years. Long before the Sun appeared, earlier generations of stars had already lived and died, producing many of the heavier elements that later became planets, oceans, bones, and blood. Your body is therefore recent in arrangement, but ancient in material. Some of its atoms were created in the early universe, while others were forged inside stars that vanished before Earth existed. Cosmic time also extends far beyond the past. The present era of bright stars may represent only an early chapter when compared with the enormous future predicted by many models. The last stars could persist for trillions of years, and remnants may survive for periods so vast that the current age of the universe would seem almost negligible beside them. Against this scale, an individual life appears impossibly brief, but brevity is not the same as insignificance. Duration alone does not measure complexity, awareness, or meaning. A flash of lightning is shorter than a stone's existence, yet it can illuminate an entire landscape. In a similar way, your consciousness occupies only a narrow interval, but within it, the universe gains a local ability to observe, question, remember, and form a model of its own history. Matter that once drifted without thought has become capable of asking where it came from. The stars do not know how old they are, but you can calculate their ages. Ancient light does not understand the distance it has traveled, but your mind can receive it and reconstruct the journey. Cosmic time makes your life look small because it reveals how little of the universe's history you personally occupy. Yet it also makes your existence extraordinary, because for one brief fraction of that history, ancient matter has awakened into something able to notice the scale surrounding it. Your life may be less than a heartbeat on the cosmic calendar, but it is a heartbeat in which the universe becomes aware that it has a past. How the speed of light connects space and time. A beam of light does more than cross the universe quickly. It quietly determines how distance and duration fit together. Before relativity, space and time were usually treated as separate backgrounds. Space told you where something happened, while time told you when. The speed of light revealed that nature does not keep these two measurements independent. Because every observer in empty space measures the same speed for light, even when the observer or the light source is moving, changes in measured distance must be balanced by changes in measured time. Otherwise, different observers would obtain different values for light's speed. This is why the speed of light acts almost like a conversion rule between space and time. A distance can be expressed through the amount of time light requires to cross it, which is why astronomers speak of light seconds, light years, and other light travel distances. 1 light year is not a duration, but the distance light travels in a year, showing how naturally cosmic measurements join the two ideas. The connection is deeper than convenient language. Light establishes the causal structure of the universe. When an event occurs, its influence cannot spread outward faster than light. The region that can receive that influence grows as time passes, creating a boundary between places that can be affected and places that remain unreachable for the moment. Physicists represent this with a light cone. Events inside the cone may be connected through signals or physical causes, while events outside it are too far apart for any information traveling at or below light speed to link them in the available time. This means light does not merely illuminate events. It determines which events can have relationships at all. If the sun changed, Earth could not respond until sunlight and gravitational information had crossed the intervening distance. If two events are separated too widely in space and too narrowly in time, neither can be the cause of the other. Different observers may disagree about the distances and durations between events, yet they agree on this deeper causal order. They agree about which connections are physically possible, because the speed of light remains the same anchor for everyone. The universe, therefore, does not contain space on one side and time on the other, joined only by human clocks. It contains space-time, a structure in which light traces the boundaries of communication, influence, and knowledge. Every message you receive, every image formed in your eyes, and every observation made by a telescope arrives along one of these permitted paths. Light is not simply the fastest traveler inside reality. It is the thread that stitches where to when, deciding how far the universe can reach during any given interval, and reminding you that distance is never only about separation. It is also about how long connection must take. Why moving faster through space means moving slower through time. The faster you race across space, the less time your own journey contains when compared with someone who follows a slower path. This statement can sound as though motion somehow damages a clock, but the effect reaches far deeper than machinery. Every physical process traveling with you changes together. Radioactive decay, chemical reactions, electrical activity, and biological aging. Nothing feels unusual inside the moving system, because your heartbeat and thoughts remain synchronized with the clock beside you. The difference appears only when two travelers who follow different motions compare how much time has accumulated for each of them. The reason can be understood through the geometry of space-time. Between two meetings, different travelers can take different routes, just as two people can cross a landscape along paths of different lengths. In ordinary space, a longer route usually requires more travel. In space-time, however, a path involving greater motion through space can contain less elapsed time for the traveler. Speed changes how a journey is divided between its spatial and temporal parts. You do not feel yourself trading time for space, but the total structure of the route produces that result. Nature demonstrates this with particles called muons. Many muons are created high in Earth's atmosphere when cosmic rays collide with atoms. When muons are studied at rest, they decay so quickly that most should disappear before reaching the ground. Yet large numbers survive the journey because they move at speeds close to that of light. From Earth's perspective, their internal decay process runs more slowly, allowing them to travel farther than their ordinary lifetime seems to permit. From the muon's perspective, its own decay proceeds normally, while the thickness of the atmosphere along its direction of motion is reduced. Both descriptions predict the same arrivals at the surface, and experiments repeatedly confirm them. This is not an optical illusion caused by delayed signals. When high-speed clocks or unstable particles return to a common location, the differences remain in the physical records. The phrase, "moving faster through space means moving slower through time," is useful, but it should not suggest that a person possesses a fixed tank of motion that is mechanically divided. The more precise truth is that space and time are joined, and different paths through that union contain different amounts of personal duration. At low speeds, the difference is so small that human life appears to share one rhythm. Near light speed, the effect becomes impossible to ignore. A traveler could cross a vast distance while experiencing far less time than those who remain behind. Not because time was switched off, but because the traveler's route through space-time was genuinely shorter in duration. Motion therefore changes more than where you arrive. It changes how much of your own existence lies between departure and return. How Einstein changed the meaning of time forever. In 1905, a young patent office employee removed time from the invisible throne it had occupied for centuries. Before Einstein, the dominant picture came from Isaac Newton. The universe possessed an absolute time that passed uniformly everywhere, independent of matter, motion, or observation. Clocks could be imperfect, but behind them was assumed to be one true cosmic rhythm shared by every event. Einstein replaced that comforting idea with something far more radical. He began by taking two principles seriously. The laws of physics should work the same way for observers moving steadily, and the measured speed of light should not depend on the motion of the source or observer. To preserve both, time could no longer remain universal. Observers moving relative to one another would measure durations differently, disagree about the lengths of moving objects, and even disagree about whether distant events happened simultaneously. Einstein illustrated the issue with imagined clocks, trains, platforms, mirrors, and flashes of light, showing that simultaneity is not a fact floating independently in the universe. To say that two distant events happened at the same time, observers must define how separated clocks are synchronized, and motion changes the result. This was more than a correction to clockmaking. It meant that time belongs partly to the observer's state of motion. A few years later, Hermann Minkowski expressed Einstein's theory through a unified geometry of space-time, where an event is defined by both its location and its time. Einstein then pushed the transformation further with general relativity. He realized that gravity could be described not as an ordinary force traveling through fixed space, but as the curvature of space-time created by mass and energy. Planets follow paths through that curvature. Light bends near massive objects, and the rates of clocks depend on gravitational conditions. Time was no longer an independent stage upon which the universe performed. It had become an active part of the performance, shaped by what the universe contained. These ideas initially seemed remote from everyday life, yet they produced predictions that observation later confirmed. The unusual orbit of Mercury, the bending of starlight, gravitational redshift, gravitational waves, and many other effects. Einstein did not claim that time was imaginary, or that every observer could invent reality freely. Relativity is precise because it provides rules for translating between different measurements and identifies quantities on which observers still agree. What changed was the belief that nature must privilege one viewpoint. There is no single perspective from which all distances, durations, and simultaneous events receive their final meanings. Each observer carries a valid local account, and the laws connect those accounts without reducing them to one master clock. Einstein's revolution was therefore both scientific and philosophical. He showed that some features of reality that feel absolute may arise from the limited path of the observer. Time did not disappear after Einstein. It became more intimate, more flexible, and more deeply woven into the universe. Every clock now tells not the time, but its time. The duration recorded along one particular journey through a cosmos where there is no view from nowhere. Why two people can experience different amounts of time. Two people can leave the same place, reunite years later, and discover that one has genuinely lived through less time than the other. The clearest way to understand this is not to imagine time as a universal substance flowing equally around everyone, but to think of each person tracing a different route through space-time. Suppose one twin remains on Earth while the other travels to a distant destination at an extremely high speed, turns around, and returns. During the journey, each person may describe the other as moving, which seems at first to create a contradiction. Why should only the traveler be younger when they meet again? The answer lies in the shape of their complete journeys. The twin who stays behind follows one largely continuous path, while the traveler changes direction and switches between different states of motion in order to return. Their situations are therefore not perfectly symmetrical. When both clocks are finally brought together, there is no disagreement left to debate. The traveling clock has recorded less elapsed time, and the traveler's body has undergone correspondingly less aging. Acceleration is important because it allows the reunion and breaks the apparent symmetry, although the final difference depends on the full paths rather than on a clock being physically damaged during acceleration. You would not feel your own time becoming slower aboard the spacecraft. Your thoughts, breathing, metabolism, and watch would all proceed normally beside you. Only the later comparison would reveal that another person's path contained more duration. This means age is not determined by a hidden cosmic clock shared equally by all lives. Two people may begin together, separate, and return carrying different amounts of personal history, not because one lost time, but because each traveled through reality along a different route. How satellites prove that time. Dilation is real. Navigation satellite can become a laboratory for relativity simply by carrying an extremely accurate clock around Earth. Atomic clocks in orbit do not tick at precisely the same rate as similar clocks on the ground, Because a satellite experiences a combination of motion and changing gravitational conditions, scientists can predict these differences, track the spacecraft's orbit, exchange signals with it, and compare its clock with reference clocks on Earth. One of the most revealing experiments began with an accident. In 2014, 2 Galileo navigation satellites were placed into more elliptical orbits than intended, causing them to move repeatedly closer to and farther from Earth. As their altitude changed, the strength of Earth's gravity at their location changed as well, producing a small, regular variation in the rate of their onboard atomic clocks. Instead of discarding the unusual orbits as scientifically useless, researchers studied clock data collected over hundreds of days and compared the observed pattern with the prediction of general relativity. The clocks changed rate in the way Einstein's theory said they should, allowing one of the most precise satellite-based tests of gravitational redshift ever performed. The result was not a visual illusion, a faulty signal, or a philosophical interpretation. It was a repeating difference recorded by physical clocks as the satellites moved through changing gravitational conditions. Satellites are especially valuable for such tests because they travel continuously through environments that cannot be reproduced easily in a laboratory while remaining accessible through radio and laser measurements. Every orbit becomes another opportunity to ask whether nature follows the predicted rhythm. The answer, within the precision of these experiments, has repeatedly been yes. Time dilation is not an imaginative effect that appears only near black holes or in science fiction. It is measurable above Earth, written quietly into the ticking of machines circling over your head. Why GPS would fail without Einstein's theory of time? Every time your phone finds your location, it depends on clocks being corrected for a universe in which time does not pass equally on Earth and in orbit. GPS satellites continually transmit radio signals containing the time of transmission and information about the satellite's position. Your receiver compares signals from several satellites, estimates how long each one traveled, and converts those travel times into distances. Because radio waves move at the speed of light, even an error of a few billionths of a second can shift the calculated distance by meters. The system therefore requires extraordinary timing precision. GPS satellites orbit high above Earth, where weaker gravity makes their atomic clocks run faster than clocks on the surface. Their orbital motion produces an opposing effect that makes them run more slowly, but the gravitational effect is larger. Combined, satellite clocks would gain about 38 microseconds per day relative to ground clocks if engineers did not account for relativity. That sounds insignificant beside an entire day, yet light can travel more than 10 kilometers during that tiny interval. The positioning error would therefore grow rapidly, making reliable navigation impossible after a short time. Engineers solve the problem by adjusting satellite clock frequencies before launch and applying additional relativistic corrections during operation, including changes associated with orbital shape and Earth's rotation. GPS is not merely a system that happens to agree with Einstein after the fact. It is designed around his predictions because it cannot function accurately without them. The same timing network supports aviation, shipping, emergency response, telecommunications, banking, electrical grids, and scientific measurements, often without the user realizing that relativity is involved. When a map guides you along an ordinary road, you are relying on signals from moving clocks high above the planet, each corrected for the way its journey changes time. Einstein's theory may appear abstract when written in a textbook, but without it, the small blue dot representing you would soon begin to wander away from where you actually stand. How clocks run differently at different heights. A clock placed on the top shelf of a room will eventually move ahead of an identical clock resting on the floor. The difference is unimaginably small, yet modern atomic clocks can detect it because height changes how deeply a clock sits within Earth's gravitational field. Closer to the ground, where gravity is slightly stronger, less time accumulates than it does at a higher position. This does not happen because gravity interferes with the gears or electronics of a clock. Every physical process at the lower height proceeds by the same slightly reduced amount when compared with the higher one, including atomic vibrations, chemical reactions, and biological activity. For centuries, such a claim would have been impossible to test because ordinary clocks were not precise enough. Today, experimental clocks can compare the behavior of atoms so accurately that researchers have measured gravitational time differences across height changes smaller than a meter. Two clocks can begin side by side, be separated vertically for a period, and then show a tiny disagreement when compared again. The higher clock has experienced slightly more elapsed time. This effect is often described as gravitational time dilation, but the word dilation can make it sound as though time is being stretched like fabric. A better way to imagine it is that different locations contain different amounts of duration between the same comparison events. On the scale of daily life, the difference is too small to influence your schedule, but over greater height differences or longer periods, it becomes important. National timing laboratories must consider elevation when comparing their most accurate clocks, because a clock moved to a mountain would gradually drift relative to one near sea level. There is no perfectly level ocean of time surrounding Earth. Every staircase, tower, valley, and mountain places matter within a slightly different temporal environment. The world seems synchronized only because human senses cannot detect the quiet disagreement. Beneath that appearance, even the height of a table is enough to change how much future a clock receives. Why your feet? Age differently from your head. You are never exactly the same age from the top of your body to the bottom. When you stand upright, your feet are closer to Earth's center than your head, which means they experience slightly stronger gravity and accumulate slightly less time. Your head therefore ages faster than your feet, although the difference during an entire human lifetime is far smaller than anything your body could feel or display. It would amount to only a tiny fraction of a second, depending on your height, where you live, and how much time you spend standing, sitting, lying down, or moving between elevations. This does not mean the cells in your face suddenly become old while your toes remain young. Locally, every part of you functions normally. A heartbeat measured beside your chest, a chemical reaction inside your foot, and a nerve signal traveling through your brain all appear ordinary in their own immediate surroundings. The difference emerges only through an extremely precise comparison between processes that remained at different gravitational heights. In principle, a clock attached near your head and another near your feet would slowly separate in their readings. The upper clock would move ahead because it occupies a slightly weaker gravitational field. Your body therefore spans more than space. It spans a minute range of elapsed time. This idea feels strange because you experience yourself as one unified present. Your nervous system binds sensations from different regions into a single body, concealing delays and physical differences that would otherwise fragment experience. Yet nature does not recognize your body as one perfectly synchronized object. Every cell follows a path determined by its position and motion. If you spent years on the top floor of a skyscraper, while another person lived at its base, you would also accumulate slightly more time than they did, though still not enough to notice biologically. The effect is real, but gentle, turning the human body into a quiet demonstration of curved space-time. You stand upright, believing every part of you shares one age, while the universe gives your head and feet subtly different histories. Why the past feels fixed, but the future feels open. The past feels like a locked room because evidence from it surrounds you, while the future arrives with no records attached. You can examine an old photograph, reread a message, touch a scar, or remember the consequences of a choice. And all these traces constrain what you can honestly believe happened. The future offers nothing comparable. You can plan, predict, and imagine, but several outcomes may still fit everything you currently know. This difference begins with causality. Earlier events influence later ones by leaving physical changes behind. Light reaches a camera, sound alters a recording, experience modifies the brain, and actions reshape the environment. These effects create an expanding network of evidence that makes the past increasingly difficult to change in interpretation, without contradicting something that remains. The future has not yet produced such a network, so the mind represents it as a field of competing possibilities. Neuroscience reflects this asymmetry. When you remember, the brain rebuilds a scene using stored fragments linked to a particular event. When you imagine what may happen, many of the same systems are used, but they recombine old fragments into new arrangements. A remembered kitchen may become the setting of a future conversation. The face of someone you know may be placed into a situation that has never occurred. The future feels open, partly because the brain can construct several plausible simulations without possessing evidence that selects only one. This openness is not proof that every outcome is physically possible or that human choice escapes all prior causes. Your body, circumstances, habits, and the laws of nature already limit what can happen. Yet limitation is different from knowledge. A chess game may follow strict rules while still containing many possible moves from the current position. Only after a move is made does the board preserve which path was taken. Emotion strengthens the contrast. Regret attaches to events whose consequences already exist, while hope and anxiety attach to events whose details remain unresolved. You can reinterpret what the past means, but you cannot prevent it from having occurred. You can influence the future, but you cannot remember it as fact. The boundary between them is therefore not simply a line on a clock. It is the difference between a world full of traces and a world still lacking them. Behind you lies evidence. Ahead of you lies uncertainty. And your mind experiences that uncertainty as possibility. How atomic clocks measure time with incredible precision. The world's most accurate clocks do not listen for ticking gears. They listen to atoms repeating the same microscopic rhythm with astonishing consistency. An atomic clock begins with a simple idea. Instead of measuring time through a pendulum, spring, or rotating planet, use a transition inside an atom that occurs at a highly stable frequency. In the international definition of the second, cesium-133 atoms provide the reference. When exposed to microwave radiation at exactly the right frequency, the atoms shift between two closely related energy states. The clock continually adjusts its microwave signal until it produces the strongest response from the atoms, using that resonance as a natural standard. After counting 9,192,631,170 cycles of this radiation, the clock declares that 1 second has passed. The atom is not a tiny clock with hands hidden inside it. It is a reproducible physical system whose behavior can be recreated in laboratories around the world. Modern optical clocks go even further by using frequencies of visible or ultraviolet light, which oscillate far more rapidly than microwaves. Because they can divide a second into vastly more cycles, they offer finer measurement, much as a ruler with more markings can resolve a smaller distance. Scientists trap and cool atoms, or ions, so that thermal motion does not blur the signal, isolate them from stray electric and magnetic fields, and compare their rhythms with lasers of extraordinary stability. The result is a clock so precise that some experimental designs would lose or gain less than a second over periods far longer than the present age of the universe, assuming their performance could be maintained continuously. Such precision is not created to make your wristwatch more impressive. Atomic clocks coordinate communication networks, establish international time, support navigation, test fundamental physics, and allow researchers to measure tiny changes in gravity and elevation. They reveal that a second is no longer defined by looking at the sky and dividing a day. It is built from a repeated quantum event, counted so carefully that the quiet behavior of atoms becomes the rhythm by which civilization organizes the world. Why there is no perfect clock anywhere in the universe. Every clock eventually reveals the conditions surrounding it, which is why no device can measure time with absolute perfection. A mechanical clock is affected by friction, temperature, vibration, and wear. A quartz clock depends on a crystal, whose frequency shifts slightly as its environment changes. Even atomic clocks, which use remarkably stable transitions inside atoms, must contend with thermal radiation, stray magnetic fields, collisions, laser noise, imperfect electronics, and the unavoidable statistical uncertainty that comes from measuring a finite number of particles. Engineers can reduce these disturbances, compare multiple clocks, and correct known biases, but they can never place a clock completely outside physical reality. A perfect clock would need to produce identical intervals forever, remain unaffected by motion and gravity, exchange information without delay, and be read without disturbing it. Nature provides no such object. Measurement itself also introduces limits. To know a clock's frequency, scientists must observe repeated cycles over some duration. Shorter observations give less certainty, while longer observations allow small instabilities to accumulate. Quantum systems add another layer because individual measurement outcomes contain unavoidable fluctuations. Using more atoms, stronger control, and clever entanglement techniques can improve precision, but no finite experiment produces infinite certainty. There is also a deeper problem with the idea of one flawless clock. A clock records its own local history. Move it, raise it, accelerate it, or place it near a different distribution of mass, and it may accumulate a different duration from another clock without either one being defective. Scientists therefore build timescales by combining data from many high-quality clocks, rather than trusting a single sacred instrument. International atomic time is formed from an ensemble distributed across laboratories, with statistical methods used to create a stable collective reference. The best timekeeping is not the discovery of a perfect rhythm hidden beneath the universe. It is the careful comparison of imperfect physical systems whose errors can be understood and reduced. This makes every clock both an instrument and a witness. It tells you not only how many cycles have passed, but something about the environment and path through which it traveled. Perfection remains unreachable because a clock can never stand outside the universe it is trying to measure. How your brain divides reality into separate moments. Your experience feels continuous, yet the brain may understand the world by cutting an unbroken stream of information into meaningful events. There is no single internal camera recording every instant with equal detail. Instead, different neural systems sample, group, and update information over different timescales. Vision can detect rapid changes. Speech comprehension must hold sounds long enough to form words, and memory may organize minutes or hours around changes in place, purpose, or emotion. The brain appears to create event boundaries whenever something important shifts. A person enters the room, a conversation changes subject, an action reaches its goal, or an unexpected sound interrupts the scene. These boundaries help the mind decide which details belong together and which should be stored as a new episode. Experiments show that people often remember information near event boundaries differently from information in the middle of a stable activity, suggesting that the brain updates its internal model when the situation changes. This process is useful because reality contains far more detail than you could preserve. By dividing experience into units, the brain can summarize what happened, predict what is likely to come next, and retrieve memories without replaying every sensory signal. Perception itself also uses short integration windows. Two flashes presented very close together may be experienced as one, while sounds arriving within a certain interval can be fused into a single syllable or rhythm. These windows are not identical for every sense or task, so there is probably no universal frame rate of consciousness. The idea that the mind sees reality as a sequence of fixed snapshots is too simple. A better picture is a collection of overlapping processes, each gathering information for as long as necessary to identify motion, language, danger, or meaning. Attention can alter which boundaries become noticeable. When deeply absorbed, several events may be grouped into one broad episode. When alert to change, the same period may be divided into many smaller segments. Your sense of separate moments is therefore partly an act of organization. The world does not arrive with clear lines drawn between one experience and the next. Your brain places many of those lines itself, quietly turning continuous change into scenes, actions, and memories that a human mind can understand. Why time slows down during an emergency. In an emergency, the world can seem to open into extra seconds that were never available before. A car turns suddenly into your path, something heavy begins to fall, or a stranger shouts, and your mind appears to enter a slower version of reality. The outside world has not changed speed. What changes is the way your brain allocates its limited resources. Ordinary perception relies heavily on prediction. Because most moments are familiar, the brain can process them efficiently without examining every detail. An emergency destroys those expectations. The nervous system detects a sharp mismatch between what it predicted and what is actually happening, forcing attention, vision, hearing, and movement planning to update rapidly. Systems linked to adrenaline and noradrenaline increase alertness, while unnecessary thoughts are temporarily pushed aside. Instead of drifting through a familiar scene, you begin making a chain of urgent calculations. Where the danger is moving, how close it is, which direction remains open, and what your body must do next. Each decision becomes a separate mental event, so the interval can feel unusually full. Some models of time perception suggest that high arousal may also increase the rate at which the brain registers internal changes, making more subjective units seem to fit inside the same measured duration. This idea is still debated, and research does not show that people gain a supernatural ability to watch events frame by frame. Emergency responses can improve certain rapid reactions while damaging judgment, narrowing vision, and causing people to miss information outside the immediate threat. The sensation of slowed time is therefore not proof that the brain has accelerated equally in every way. It is the result of a survival system reorganizing experience around action. The strange gift of the emergency is that it reveals how flexible your present can become. A second measured by a clock remains unchanged, yet when every fraction of it carries a possible consequence, your mind gives that second far more space. How attention changes the speed of time. Time becomes most visible when you decide to watch it. Psychologists often study this through prospective timing, situations in which people know in advance that they will later be asked how long an interval lasted. Under these conditions, attention behaves almost like a gate, when much of your mental focus is directed toward duration. More timing information is registered, and the interval tends to feel longer. When attention is consumed by a demanding conversation, a difficult game, or a complex task, fewer resources remain available for tracking duration, so the same interval may seem shorter. Laboratory experiments demonstrate this by asking participants to estimate time while performing tasks of different difficulty. As the competing task demands more concentration, people often underestimate how much time has passed. This does not mean the brain contains one literal stopwatch hidden in a single region. Time estimation emerges from several systems involving attention, working memory, bodily signals, and patterns of change. The mind must notice that an interval began, continue updating its estimate, and preserve enough information to judge when it ended. Interrupt any part of that process, and experienced duration shifts. Emotional attention can alter it as well. A threatening image may hold the mind so strongly that its presentation seems longer than that of a neutral image, while an absorbing activity can make a much larger block of time disappear from awareness. Even switching attention repeatedly has an effect, because each interruption forces the brain to rebuild its estimate. This is why checking the clock does not merely reveal how slowly time is passing. The act of checking can help produce that slowness. By returning attention to duration again and again, your sense of time is therefore not a passive reading of an internal instrument. It is partly a record of what your attention was allowed to notice. The clock counts every second equally, but consciousness gives those seconds different weights depending on where it looks. Why new experiences make life feel longer? A single unfamiliar day can occupy more space in memory than a month spent repeating the same routine. Novelty changes how the brain represents experience, because an unfamiliar environment cannot be reduced immediately to an existing pattern. New streets, faces, sounds, rules, and decisions require closer observation And the hippocampus helps separate these details into distinct memory representations, rather than blending them with what is already known. This process is sometimes called pattern separation. Similar events are stored with enough difference that they can later be recalled as individual episodes. Familiar periods are more easily compressed because the brain can summarize them with a general script. You may remember that you worked, traveled home, ate, and slept without retaining what made one Tuesday different from another. A first visit to another country, by contrast, may leave dozens of separate scenes, each with its own sensory and emotional character. When you later estimate how long the experience lasted, the number of recoverable changes can make the period feel expanded. This produces what is sometimes called the vacation paradox. A busy trip may seem to pass quickly while you are living it, because your attention is engaged, yet it can feel surprisingly long in retrospect because it created many distinct memories. Novelty can also cause brief distortions in the moment. In oddball experiments, an unusual image appearing among repeated images is often judged to have lasted longer, even when every image was shown for the same duration. The brain appears to allocate extra processing to the unexpected event, giving it greater subjective weight. But novelty alone is not enough to enrich a life. Experiences that are overwhelming, meaningless, or poorly attended may leave little coherent memory. What extends remembered time is manageable difference combined with attention. A new skill practiced carefully, a familiar route taken in another direction, or a conversation that breaks an old assumption. You cannot add hours to the calendar through novelty, but you can prevent long periods from being stored as one indistinct block. A life feels fuller not only when more events occur, but when the mind has enough reasons to keep them separate. How your brain creates the feeling of now. The present moment feels immediate, yet your brain must quietly build it before you can experience it. Light, sound, touch, and signals from inside your body do not arrive at the same speed, and they are not processed by identical neural pathways. A flash reaches your eyes almost instantly, while a sound travels more slowly through the air, and a touch from your hand must move through nerves before reaching the brain. If awareness displayed every signal the moment it arrived, the world would feel broken into poorly synchronized pieces. Instead, the brain gathers information across a brief interval and decides which signals probably belong to the same event. This process allows a person's moving lips and voice to feel united, even though the visual and auditory information reach you at slightly different times. Experiments show that the brain can sometimes revise its interpretation of an event after receiving later information, a process known as postdiction. A second flash, sound, or movement can alter what you believe occurred a fraction of a second earlier, revealing that conscious experience is not always finalized immediately. The brain also predicts what should happen next, using recent patterns to stabilize motion and prepare action. Your sense of now is therefore neither a perfect snapshot nor a fixed point. It is a carefully edited window containing a small amount of recent information, corrected by what arrives afterward, and shaped by what the brain expects to occur next. This window must be wide enough to recognize a spoken word, follow a gesture, and understand that one event caused another, yet narrow enough to let you respond before conditions change. The present feels effortless because the construction remains hidden. You do not notice the delays, comparisons, and corrections taking place beneath awareness. You receive only the finished scene. What you call now is the brain's most useful agreement about what is happening. A moment assembled slightly late, but delivered with such precision that it feels as though reality and consciousness arrived together. Why repetitive years seem to disappear quickly. Year can remain on the calendar for 12 full months and still leave behind almost nothing your mind can clearly enter again. Repetition causes this strange compression because autobiographical memory does not preserve every ordinary day as a separate record. When experiences repeatedly follow the same structure, the brain begins storing their shared pattern rather than maintaining detailed versions of each occurrence. You remember that you traveled to work, completed familiar tasks, ate similar meals, and returned home. But the individual mornings gradually merge into one general script. Psychologists sometimes describe this shift as semanticization. Richly detailed episodes lose some of their original context and become broad knowledge about what life was usually like during that period. This is efficient because the brain does not need hundreds of nearly identical memories to guide future behavior. Yet the same efficiency makes time appear to vanish in retrospect. When you look back over a repetitive year, the mind searches for distinctive scenes that can divide it into chapters. If few details separate one month from another, the entire period may be represented by only a handful of summaries. The year did not contain fewer hours, and it may not have felt fast while you were living it. Its apparent shortness emerges later, when memory finds too few independent moments to reconstruct its length. Repetition can also weaken contextual cues. A memory becomes easier to locate when it contains a unique place, goal, emotion, or social situation. When the surroundings and routines remain unchanged, memories compete with one another because they share the same cues, making specific days difficult to retrieve. This is why an unusual interruption, a sudden trip, a new responsibility, an unexpected visitor can remain vivid while the weeks around it dissolve. The disappearing years are not proof that your life moved faster. They reveal that remembered duration depends partly on how clearly experience was divided and preserved. Routine can provide safety, skill, and stability, but when every day is stored under the same mental label, months may pass into memory without leaving visible edges. The calendar keeps every date. The mind keeps only enough difference to know that something changed. How childhood creates a different sense of time. For a child, next month can feel almost as distant as another lifetime, because the mind's ability to represent time is still being built. Young children do not begin with an adult understanding of minutes, weeks, birthdays, and years. They gradually learn these ideas through language, routines, clocks, calendars, and repeated experiences of waiting. Before those concepts become stable, time is often understood through events rather than numbers. After lunch, before bedtime, when school ends, or when a parent returns. This makes duration deeply dependent on emotion and uncertainty. 10 minutes can feel enormous when a child does not know exactly what will happen during them, while an afternoon of play may pass without being measured at all. The developing prefrontal cortex also affects planning, impulse control, and the ability to imagine distant rewards. Adults can tolerate a delay by placing it inside a larger plan, but children often experience waiting as a more immediate conflict between desire and absence. Their future horizon is shorter, and distant events are harder to picture with detail, which is one reason promises such as next year can feel vague and almost unreal. Childhood time is also structured largely by other people. Adults decide when a child wakes, eats, leaves, returns, and goes to sleep. Because the child has limited control over these transitions, waiting can feel less like choosing to pause and more like being held inside an interval whose ending belongs to someone else. As language, memory, and self-control develop, the child becomes better at arranging events into timelines, estimating duration, and imagining a future self who will eventually reach a desired moment. Even then, emotional events can dominate the sense of time. A first night away from home, an approaching birthday, or the final hour before a holiday may expand because anticipation fills every part of attention. Childhood, therefore, does not contain a slower physical clock. It contains a mind still learning how to measure, predict, and emotionally manage duration. The long days of childhood may seem mysterious when remembered from adulthood, but they were lived by someone for whom time was not yet an invisible schedule running in the background. It was something encountered directly through waiting, wanting, routines, and the gradual discovery that every not yet eventually becomes now. Why waiting makes every minute feel longer. Waiting becomes painful when the future matters, but refuses to reveal exactly when it will arrive. A delayed message, a medical result, a late train, or the sound of footsteps outside a closed door can make a short interval feel strangely enlarged because your mind cannot settle into action. When you know what to do, attention moves toward the task. When you are waiting, attention remains suspended between the present and an event that has not yet occurred. The brain repeatedly checks for change. Was that the notification? Has the line moved? Is the person coming? Each unsuccessful check becomes a separate mental marker, dividing the interval into smaller and more noticeable pieces. Uncertainty intensifies the effect. A clear 5-minute delay is often easier to tolerate than an unknown delay that may end in 1 minute or 20 because predictable waiting can be placed inside a plan. Uncertain waiting keeps the nervous system partially prepared, unable to relax and unable to respond. A lack of control also matters. Choosing to pause can feel peaceful, while being forced to pause often feels like time has been taken from you. This is why progress bars, appointment times, and visible cues can reduce frustration even when they do not make the wait physically shorter. They give the mind evidence that the future is approaching. Emotion shapes the interval as well. Anticipation of something pleasant may make waiting restless but hopeful, while fear of bad news can fill every minute with imagined outcomes. In both cases, the event ahead occupies more attention than the world immediately around you. The clock has not slowed, yet the present begins to feel like an obstacle standing between you and what matters. Waiting teaches you that duration is not experienced only as length. It is also experienced as distance from resolution, and a minute feels longest when you are ready to move, but reality has not yet opened the door. How happiness can make hours disappear. Joy can remove the edges from an afternoon until you look up and discover that several hours have quietly passed. Happiness does not speed up the external clock, but it changes how closely you monitor yourself and the passing interval. During a rewarding conversation, a celebration, a creative activity, or time spent with someone you trust, the brain is occupied with meaningful signals rather than with measuring duration. Positive emotion can broaden awareness, making you more receptive to ideas, social cues, and possibilities, while reducing the constant internal question of how long the experience has lasted. Reward-related systems reinforce engagement by giving the current activity value, encouraging you to remain inside it rather than search for an escape. This creates fewer moments of temporal self-checking. You do not repeatedly ask whether the hour is ending, because the hour is not something you are trying to survive. Happiness can also soften self-consciousness. When you feel safe and connected, less mental energy may be spent monitoring threat, discomfort, or how you appear to others. Experience becomes less divided into before, during, and after, allowing events to blend into a smooth and satisfying whole. Yet there is an important paradox. A happy period may feel brief while it is happening because you pay little attention to duration, but it can later feel rich and substantial if it produced vivid memories. A joyful holiday may seem to end too quickly, while its scenes remain available for years. Pleasure, therefore, changes time differently depending on whether you judge it from inside the experience or from memory afterward. Happiness does not erase hours. It removes your need to count them. This may be why some of the most valued moments in life seem to disappear as they occur. Their apparent shortness is not evidence that they contained less living, but that for a while you were so fully welcomed by the present that you stopped asking when it would be over. Why pain changes. Your experience of time. Pain can make a single minute feel physically larger because the brain treats every moment of discomfort as information that may require protection. Pain is not a simple signal traveling from damaged tissue to a passive mind. It is an experience constructed from sensory input, attention, emotion, expectation, and the brain's judgment about threat. When pain begins suddenly, attention is pulled toward the body with unusual force. The mind tracks changes in intensity, searches for a cause, and prepares movements that might reduce harm. Because each fluctuation becomes significant, the interval can feel densely filled and therefore longer. Anticipation can magnify this effect. Knowing that a painful procedure is approaching may stretch the seconds before it occurs, while uncertainty about when the next wave of pain will arrive can prevent the nervous system from settling. Fear often increases the perceived threat, and greater threat can intensify both pain and duration. Safety can work in the opposite direction. Clear information, trust in a caregiver, and a sense of control may not remove the physical cause, but they can reduce the alarm surrounding it. Chronic pain creates a different temporal world. Instead of one sharp episode with a clear ending, it can make the future difficult to imagine because tomorrow is expected to contain the same discomfort. Days may feel slow in the moment, yet months can lose their boundaries when activities become limited and routines narrow. Pain can also disturb sleep, concentration, and memory, weakening the ordinary landmarks by which a person organizes time. This is one reason persistent pain affects far more than the injured body part. It changes planning, identity, and the emotional distance between now and later. Distraction sometimes shortens painful intervals by reducing the attention available for monitoring sensation. While focused medical techniques can help people observe pain without adding as much fear or resistance, these approaches do not imply that pain is imaginary. They reveal that pain and time are both shaped by how the brain evaluates what is happening. A painful second feels long because the body is asking consciousness not to look away, turning duration itself into part of the warning. How depression can make the future feel far away. Depression can make tomorrow feel less like a place you are approaching and more like a distant country you no longer know how to reach. This is not simply pessimism or a refusal to think positively. Research suggests that depression can alter perspection, the mental ability to construct personally meaningful future events. When you imagine an ordinary day ahead, your brain normally combines memory, emotion, and knowledge into a detailed simulation, where you might be, who may be present, what you could feel, and why the event matters. During depression, especially positive future scenes may become less specific, less vivid, and harder to generate. You may understand intellectually that life can change while finding it difficult to feel that change as something real and emotionally available to you. Anticipatory pleasure can also weaken. An activity that might be enjoyable when it occurs may produce little motivation beforehand, so the path toward it feels empty. This helps explain why simple plans can seem strangely remote. The problem is not always that the future is expected to be terrible. Sometimes it appears blurred, emotionally flat, or disconnected from the person you are now. Depression can also encourage broad predictions such as nothing will improve, replacing detailed possibilities with one heavy conclusion. Yet these conclusions are symptoms shaped by a current state, not privileged knowledge about what will actually happen. Studies of future thinking show patterns and tendencies, not an irreversible loss of imagination. And psychological treatment can help some people rebuild more concrete ways of picturing what lies ahead. A useful future does not need to begin as a grand vision. It can return through one believable scene, a meal you may prepare, a place you may visit, or a conversation you may survive. Depression stretches the emotional distance to tomorrow, but distance is not the same as impossibility. The future can remain present in reality even when your mind temporarily loses the feeling of being connected to it. Why flow states make you forget time exists? Sometimes a difficult activity fits your abilities so precisely that the clock seems to fall out of the room. This state is known as flow, and it can appear during music, sport, writing, drawing, coding, craftsmanship, gaming, or any task that joins clear goals with immediate feedback and a challenge demanding your full skill. Flow is not merely intense happiness, and it is not passive relaxation. You remain highly active, correcting small errors and responding to changing conditions. Yet action begins to feel unusually smooth because each step tells you what the next one should be. The separation between deciding and doing becomes less noticeable. At the same time, self-conscious monitoring often fades. You stop repeatedly asking whether you are performing well, how you appear, or how much longer the task will last. That disappearance of self-evaluation matters because ordinary time awareness often depends on stepping mentally outside an activity and checking your progress against a clock. In flow, those checks become less frequent. Your cognitive resources are organized around the task's internal structure: the next note, movement, sentence, or solution. Hours can therefore seem short when you finally look back, even though the period contained intense concentration rather than emptiness. Research treats altered time perception as a common feature of flow, but it is not identical in every case. Some people report time passing rapidly, while fast and demanding activities can occasionally make individual moments feel expanded. Flow also cannot be commanded simply by trying harder. A task that is too easy invites disengagement, while one far beyond your skill may produce anxiety and confusion. The state is more likely near the shifting boundary, where difficulty requires everything you can offer without making progress impossible. Flow makes time disappear because experience becomes organized by meaningful action rather than by duration. For a while, you are not standing beside yourself measuring life as it happens. You are participating so completely that the measurement becomes unnecessary. How meditation changes the experience of the present. Meditation does not freeze you inside a perfect now. It changes what you notice while the present continues to move. In many mindfulness practices, you place attention on breathing, bodily sensation, sound, or thought, and gently return whenever the mind wanders. The purpose is not to eliminate memory, planning, or inner speech, but to recognize these events as they arise without automatically following every one of them. This can alter time perception because ordinary duration is often covered by mental movement. You rehearse an old conversation, prepare for a future problem, judge your progress, and discover that several minutes have passed almost unnoticed. During meditation, subtle changes that normally remain in the background can become clearer. The beginning and end of a breath, pressure shifting through the body, a sound appearing and fading, or an emotion changing before it receives a name. Some experiments have found that brief mindfulness practice can increase sensitivity to duration or make intervals feel longer, possibly because more attention is available for ongoing experience. Other research has found different effects depending on the meditation style, the duration being judged, and the emotional state of the participant. A recent systematic review therefore concluded that the relationship is real but complex rather than governed by one rule. Meditation may slow the felt passage of time in one context, shorten an estimated interval in another, or simply reduce the pressure associated with time. This last change may be the most important. 5 minutes can still be 5 minutes, while feeling less like a barrier that must be crossed. By observing impatience as a changing sensation rather than an order demanding immediate action, you create a small distance between duration and urgency. The present does not become endless or mystical. It becomes more detailed and less tightly controlled by the story of where you should already be. Meditation cannot stop time, but it may reveal that many moments once described as empty were quietly filled with breath, sensation, and change, waiting not to be extended, but to be noticed. Why sleep erases your awareness of passing time. You can close your eyes at midnight and seem to open them only a moment later, even though the world has moved several hours into the future. Sleep does not stop the brain or erase every form of experience. It changes the conditions required for building a continuous account of time. Throughout the night, the brain cycles through several stages, including light sleep, deep slow-wave sleep, and periods of rapid eye movement sleep in which vivid dreams are more common. During these stages, systems involved in attention, self-monitoring, and the stable recording of new autobiographical memories operate differently from the waking state. Your brain continues regulating temperature, breathing, hormones, immune activity, and the restoration of neural tissue. Yet much of this work is not organized into a story that the waking self can later retrieve. You may briefly awaken many times without remembering it, because the awakenings are too short or too poorly encoded to become durable memories. This absence of stored landmarks makes the night feel compressed. While awake, you estimate duration through changes in light, movement, conversation, bodily needs, and a sequence of remembered events. During dreamless sleep, those markers may never enter conscious memory. During dreams, unusual scenes can occur, but they are often forgotten quickly because the brain chemistry supporting stable memory formation differs from waking conditions. When morning arrives, you do not experience 8 hours collapsing into one instant. You simply find no continuous chain of remembered awareness connecting bedtime to waking. The interval feels missing because your mind cannot reconstruct how it was crossed. Sleep, therefore, reveals that the experience of duration depends on more than a functioning brain. It requires an observing self that can preserve enough of its changing state to know that time has passed. The hours were real. Your body lived through every one of them, and the brain remained active, but without a lasting narrative. The night returns to you as a quiet gap between two moments of consciousness. How anesthesia makes hours vanish instantly. General anesthesia can remove an entire operation from your experience so completely that the moment before unconsciousness seems to touch the moment of awakening. This is not because anesthetic drugs accelerate time, and it is not simply a deeper form of ordinary sleep. Sleep follows naturally recurring cycles from which the brain can often awaken in response to meaningful sounds, touch, or internal needs. General anesthesia is a medically controlled state produced by drugs that disrupt several processes required for conscious experience. Depending on the agents used, these drugs strengthen inhibitory signaling, weaken communication between distant brain regions, reduce the integration of sensory information, and prevent the brain from building a unified model of the body and surrounding world. A surgical stimulus may still produce activity in parts of the nervous system, which is why anesthesiologists monitor vital signs and often combine unconsciousness with pain control and muscle relaxation. But isolated neural responses do not necessarily become a conscious event. Awareness seems to require information to be shared across coordinated networks, rather than remaining trapped in disconnected pockets of activity. Anesthesia also interferes with memory formation. Even if brief fragments of processing occur, they may leave no accessible record afterward. This combination, the loss of integrated awareness and the failure to create continuous memory, explains why hours can seem to vanish without any felt passage. You do not wait in darkness, because waiting would require a conscious point of view capable of noticing the absence of events. You do not experience an empty interval extending slowly around you. From your perspective, there is the final moment before the anesthetic takes effect, and then the first moment in recovery, with no experience bridge between them. Rare cases of accidental awareness during anesthesia show why careful monitoring and dosing are essential, but modern practice is designed to make such events uncommon. The vanished hours demonstrate something profound about consciousness. Physical time can continue, machines can record every second, and the body can undergo complex events, while personal time disappears when the brain can no longer bind experience into an aware and memorable sequence. Why time moves slower near a black hole. Clock hovering near a black hole would return with fewer seconds recorded than an identical clock kept far away, even if both instruments worked perfectly. The cause is the extraordinary gravitational difference between their locations. A black hole concentrates a great amount of mass into a small region, producing a steep curvature of space-time. The closer a clock remains to that mass, the less elapsed time it accumulates when later compared with a distant clock. This effect is not limited to black holes, but they amplify it beyond anything found near ordinary planets or stars. Imagine a series of observers stationed at different safe distances, each sending regular flashes of light outward. Signals from the observer closest to the black hole would arrive increasingly spread apart and shifted toward lower frequencies. To someone far away, the near black hole clock would appear to tick slowly, because every new signal takes longer to climb out of the deeper gravitational region. The observer beside that clock, however, would notice nothing abnormal in their immediate surroundings. Their pulse, thoughts, and instruments would proceed normally because all local processes share the same rate. Time dilation becomes meaningful only when information is exchanged or the clocks are eventually compared. Remaining stationary extremely close to the event horizon would require enormous acceleration. Since gravity there would make hovering increasingly difficult. A freely orbiting traveler could avoid some of that effort, but their high orbital speed would introduce an additional slowing effect. Around a rotating black hole, the situation becomes even more complex because space-time itself is dragged around the object, changing which stable orbits are possible. Science fiction often uses these effects to produce worlds where a short visit corresponds to years far away, and such differences are allowed by relativity under sufficiently extreme conditions. The practical dangers, including radiation, unstable orbits, and tidal forces, would depend strongly on the black hole's mass and environment, yet the central fact remains calm and precise. A black hole does not cast a spell over clocks. It changes the geometry through which they travel. Near its darkness, time is not damaged or frozen. It simply follows a path containing less duration than the path taken by the distant universe. Why you cannot remember the exact moment you fall asleep. The instant you fall asleep is one of the few transitions in life that disappears precisely because you are crossing it. You can remember lying in bed, adjusting the pillow, hearing the last sounds in the room, and perhaps watching your thoughts become stranger and less orderly. But the exact moment wakefulness ends is usually missing. This happens because falling asleep is not a single switch that turns off at once. It is a gradual change across many brain systems. Attention weakens, awareness of the environment becomes less stable, muscles relax, and the electrical activity of the brain shifts toward patterns associated with early sleep. During this transition, thoughts often become fragmented and dreamlike, sometimes producing brief images, sounds, or the sensation of falling. Yet memory formation is also becoming less reliable. To remember an event later, the brain must not only experience it, but encode it into a form that survives the transition into another state. As sleep deepens, the networks that support deliberate attention and continuous autobiographical memory stop working together in the waking way. The final moments are therefore poorly recorded, and because awareness itself is fading, there is no clear observer left to announce. This is the instant sleep has begun. Even scientists studying sleep usually define its onset through brain waves, eye movements, and muscle activity, rather than through a person's own certainty. People often believe they remained awake longer than measurements show because light sleep can still contain thoughts and a faint sense of the room. You may already be asleep while feeling as though you are merely resting with your eyes closed. The mystery is not that sleep steals a perfectly formed memory afterward. The memory is never fully created. You approach the boundary with the tools needed to notice it, but those tools fade as the boundary is crossed. Sleep begins by quietly removing the witness who could remember its arrival. How jet lag reveals the clock hidden inside your body. Jet lag begins when the clock on the wall changes instantly, but the clock inside your body refuses to follow. After traveling rapidly across several time zones, local noon may arrive, while your brain and organs still behave as though it were early morning or the middle of the night. This conflict reveals the circadian system, a biological timing network that organizes sleep, alertness, body temperature, hormone release, digestion, and many other daily functions. Its central coordinator is a small region of the brain called the suprachiasmatic nucleus, located above the point where signals from the eyes cross. Specialized cells in the retina detect environmental light and send timing information directly to this region, allowing it to adjust the body's internal day to the outside world. Yet the adjustment is gradual. Your internal rhythms cannot normally shift by many hours in a single night, which is why you may feel wide awake at bedtime, hungry at unusual hours, or exhausted in the middle of the afternoon after a long flight. Different systems also adapt at different speeds. The sleep schedule may begin to change, while digestion, temperature, and hormone rhythms remain closer to the old time zone, creating the sense that your body is no longer acting as one coordinated whole. Traveling east is often harder than traveling west because advancing the internal clock usually requires the body to begin sleeping earlier, while delaying sleep is easier for many people. Morning or evening light can help shift the clock, but the timing matters. Light at the wrong hour may push adaptation in the opposite direction. Meals, exercise, and social routines provide weaker timing signals that can also assist. Jet lag is therefore more than tiredness caused by a flight. It is a temporary separation between astronomical time, social time, and biological time. Your watch accepts the new location immediately, but your cells continue carrying the memory of where the sun used to rise. Why your body keeps time, even without a clock. Even in a room without windows, watches, or sunlight, your body continues producing its own pattern of mornings and nights. This happens because biological time is generated from within rather than copied passively from a clock on the wall. At the cellular level, groups of genes and proteins interact in repeating cycles that last close to 24 hours. Certain genes become active and produce proteins. As those proteins accumulate, they eventually suppress the genes that created them. The proteins are then broken down, the suppression fades, and the cycle begins again. This molecular feedback loop operates in many tissues, giving the liver, heart, lungs, muscles, and other organs their own local rhythms. These peripheral clocks help schedule when the body is best prepared to process food, repair tissue, release hormones, or use energy. The brain's central clock helps keep them coordinated, but they are not silent machines waiting for instructions. Experiments in constant darkness show that humans still sleep, wake, and experience daily changes in temperature and alertness, although the rhythm usually drifts slightly because the internal cycle is not exactly 24 hours. This is why environmental cues are necessary. Light, meals, activity, and temperature reset the system each day, preventing the biological clock from slowly separating from the planet's rotation. The body's timing is also not perfectly rigid. Illness, age, shift work, irregular sleep, and eating at unusual hours can weaken coordination between internal clocks. One organ may receive signals associated with daytime, while another is being asked to behave as though it were night. Researchers are studying how this internal misalignment may affect metabolism, mood, cardiovascular health, and immune function, although the relationships are complex and differ between individuals. What is clear is that your body does not merely respond to events as they arrive. It prepares for them. Hormones begin changing before waking. Digestion anticipates usual meal times, and alertness rises and falls according to an internal schedule. You carry a system of living clocks inside you, each predicting the day before the day has fully reached it. How sunlight resets your internal sense of time. Morning light does not merely help you see the world, it tells your body which part of the day has begun. Inside the retina are specialized cells containing a light-sensitive pigment called melanopsin. Unlike the cells mainly responsible for forming images, these cells are especially important for measuring environmental brightness and sending timing information to the brain. Their signals help adjust the circadian system, influencing when you feel alert, when body temperature rises, and when the hormone melatonin begins or stops preparing you for sleep. Sunlight is particularly powerful because it is far brighter than most indoor lighting, even on an overcast day. Exposure soon after waking generally helps anchor the internal day and can gradually shift the body toward earlier sleep and wake times. Bright light late in the evening can have the opposite effect, delaying the internal night and making sleep arrive later. The result depends not only on brightness, but also on timing, duration, wavelength, and your recent light history. The same light that advances your clock in one part of the day may delay it in another, which is why scientists describe a phase response pattern rather than one simple rule. Natural daylight also changes continuously. Dawn grows brighter, midday becomes intense, and sunset softens toward darkness, providing the brain with a sequence of cues that artificial environments often flatten. When you spend most of the day under dim indoor light, and then surround yourself with bright screens and lamps at night, the contrast between day and evening becomes weaker. The body may receive an uncertain message: insufficient brightness when it should be daytime, and too much illumination when biological night should begin. Sunlight also affects mood, attention, and seasonal patterns, although these effects involve several systems and vary among individuals. It does not reset a mysterious inner stopwatch in a single instant. It gently shifts the timing of biological processes by giving the brain evidence about Earth's daily rotation. You may believe that you wake because the alarm rings, but beneath that social signal, your body is listening for something older. Every morning, light enters your eyes and quietly reminds your cells where they are within the turning day. Why humans naturally live by cycles. Your life is not organized as a straight line of identical hours. It rises and falls through overlapping waves. Human biology evolved on a planet shaped by repetition, daylight and darkness, tides, seasons, changing temperatures, and recurring opportunities for food and rest. Living systems became adapted not only to respond to these changes but to anticipate them. The most familiar biological cycle lasts roughly a day, yet it is only one layer. During sleep, the brain moves through repeating stages over shorter periods, producing several cycles across a single night. Hormones can be released in pulses rather than in a smooth, continuous stream. Alertness may rise and fall across the day. Appetite returns after intervals, and physical performance can vary depending on the hour. Longer rhythms also exist. Reproductive biology, immune activity, mood, and behavior may change across weekly, monthly, or seasonal timescales, although not every apparent pattern is controlled by a perfect internal clock. Some cycles arise from biology, others from social habits, and many emerge from interaction between the two. The 7-day week, for example, is largely cultural. Yet once work, rest, meals, and expectations are organized around it, the body can begin responding to that repeated structure. Cycles are useful because constant maximum activity would be costly and damaging. Muscles need recovery after effort. Attention benefits from alternation between focus and rest. Sleep allows different forms of maintenance and memory processing that cannot occur in the same way during waking activity. Even hunger is not simply an empty fuel gauge. It is influenced by learned meal schedules, hormones, and anticipation. The body prepares before a repeated event arrives. This is why changing a routine can produce discomfort before any real shortage or danger exists. A familiar cycle has been interrupted, and the organism must revise its prediction. Yet human rhythms are flexible, rather than perfectly mechanical. Travel, artificial light, shift work, illness, age, and social demands can pull cycles apart or force them into unusual schedules. You can stay awake through the night, eat when you are not hungry, or work against fatigue, but adaptation often carries a cost when recovery is repeatedly denied. The circular pattern of life is therefore not evidence that nothing changes. Each return is slightly different. You sleep again, but not with the same brain. Another season arrives, but you meet it with another year inside you. Human life moves forward by repeating, using cycles to preserve stability while quietly allowing change. How your heart, brain, and cells keep different rhythms. You are not powered by one internal beat, but by countless rhythms that overlap without ever becoming perfectly identical. The heart produces the most obvious pattern. A small group of specialized cells in the sinoatrial node generates electrical impulses that spread through cardiac tissue and coordinate each contraction. Yet a healthy heartbeat is not perfectly regular like a metronome. The interval between beats changes subtly with breathing, movement, emotion, and signals from the autonomic nervous system. This variation allows the cardiovascular system to respond flexibly rather than remaining locked to one pace. The brain follows a different kind of timing. Networks of neurons produce oscillations at several frequencies, from slow waves associated with deep sleep to faster activity linked with attention, perception, and active thought. These rhythms are not separate stations that turn on one at a time. They can coexist, interact, and coordinate activity across brain regions. A slower rhythm may organize when bursts of faster activity occur, helping distant groups of neurons exchange information at useful moments. Scientists can record these patterns with instruments such as electroencephalography, but no single brainwave represents one thought or emotion. The relationship is more complex. Rhythms create windows in which communication becomes more or less likely. At the cellular level, timing becomes even more varied. Calcium levels can rise and fall in repeated pulses. Genes can switch activity in cycles. Metabolic reactions can oscillate. And cells can coordinate division, repair, and signaling through chemical feedback. Some rhythms last milliseconds, others minutes, hours, or days. Organs must communicate across these different scales without forcing every process into exact synchrony. Breathing can influence heart rhythm. Heart activity can alter signals reaching the brain, and hormonal cycles can change how cells throughout the body respond. Health often depends not on perfect regularity, but on adaptable coordination. A heart locked into rigid timing can be less resilient, while disrupted neural or cellular rhythms may interfere with sleep, movement, or metabolism. This does not mean every illness is simply a broken rhythm, but it shows how deeply timing is woven into physiology. You experience yourself as one continuous being because these systems cooperate well enough to create unity. Beneath that unity, however, your body resembles an orchestra without a single drummer. Each section keeps its own tempo, listens to the others, and adjusts just enough for the larger composition to continue. How the first clocks were built from shadows. Long before time began ticking inside machines, people learned to read it from a patch of darkness moving across the ground. One of the earliest timekeeping tools was the gnomon, a vertical stick, pillar, or stone, whose shadow changed direction and length as the sun appeared to travel across the sky. In the morning, the shadow stretched far toward the west. Around midday, it became shorter. By evening, it reached toward the east. By placing marks around the gnomon, ancient observers could divide daylight into recognizable portions and estimate when work, prayer, trade, or public ceremonies should begin. Later sundials refined this idea by angling the shadow casting piece so that it aligned more closely with Earth's axis, allowing the shadow to move across our lines in a more regular way. Yet these early clocks did not measure time exactly as modern clocks do. In many ancient systems, daylight was divided into a fixed number of parts, which meant that a daytime hour could be longer in summer and shorter in winter. The device also depended on latitude, season, and the position of the sun, so a sundial designed for one place might not work accurately somewhere else. Clouds made it useless, and night removed the shadow completely. Even local noon, the moment when the sun reached its highest point, did not always occur at the same time shown by a modern clock, because Earth's orbit and tilted axis make the apparent solar day vary slightly across the year. Despite these limitations, shadow clocks represented a remarkable intellectual step. People realized that time could be inferred from predictable motion and transformed into a visible pattern. The passing day was no longer only something felt through hunger, fatigue, or fading light. It could be mapped onto stone. A shadow, normally treated as an absence of light, became one of humanity's first instruments for making the invisible structure of the day appear. Why ancient civilizations watched the sky to measure time. For early civilizations, the sky was not decoration above the world. It was the most reliable calendar they possessed. The movements of the sun, moon, planets, and stars repeated with enough regularity to organize agriculture, navigation, religion, taxation, and political life. Farmers needed to know when seasonal rains might return, when rivers were likely to flood, and when crops should be planted or harvested. Priests and rulers needed shared dates for festivals, ceremonies, debts, and public duties. Because written calendars were useful only when connected to real celestial cycles, generations of observers learned to recognize where the sun rose and set at different times of year, which constellations appeared before dawn, and how the night sky changed from season to season. In ancient Egypt, the first annual appearance of Sirius shortly before sunrise became associated with the approaching Nile flood, although the relationship was not perfectly identical every year. Egyptian timekeepers also used groups of stars known as decans to estimate the passing hours of the night as different star groups rose above the horizon. In Mesopotamia, Babylonian scholars recorded planetary motions, eclipses, and lunar patterns across long periods, building some of the most systematic astronomical records of the ancient world. Elsewhere, structures and horizon markers were aligned with solstices, equinoxes, or other important celestial events, helping communities recognize turning points in the year. These observations were not always separated into the modern categories of science, religion, and government. A prediction about the sky could also be a sacred duty or a sign of royal authority. Yet beneath the symbolism was careful empirical knowledge. Celestial events repeated, and those repetitions could be compared, recorded, and used. The heavens offered something human life could not, a pattern extending beyond one generation. By watching it patiently, civilizations transformed scattered days into seasons, and seasons into history, discovering that the sky could preserve order even when life below remained uncertain. How the moon helped humans invent the month. The month began not with a number on paper, but with a shape in the night sky slowly disappearing and returning. The moon passes through a repeating sequence of phases because its changing position relative to Earth and the Sun alters how much of its illuminated half you can see. From one new moon to the next takes about 29.5 days, a period known as the synodic month. This cycle is long enough to organize human activity, yet short enough to observe repeatedly within a season, making it one of the most natural units available to early societies. A thin crescent could announce the beginning of a new count. The full moon marked a bright midpoint. The fading crescent signaled that the cycle was nearing completion. The connection survives in language. The English words moon and month share an ancient linguistic origin, but the moon created a difficult problem for calendar makers. 12 lunar cycles total only about 354 days, roughly 11 days shorter than the solar year that governs the seasons. A purely lunar calendar therefore moves through the seasons unless corrections are added. This is why the Islamic calendar, which follows 12 lunar months without keeping them fixed to the solar year, causes religious dates to occur at different seasons over time. Lunisolar calendars, including traditional Jewish and Chinese systems, solve the mismatch by occasionally adding an extra month so that lunar dates remain connected to the agricultural year. Other civilizations gradually moved towards solar calendars, while retaining months as inherited divisions, even though their lengths no longer matched one complete lunar cycle. The modern calendar still carries the compromise. Months contain 28 to 31 days, preserving the memory of lunar counting while fitting approximately into a solar year. The moon therefore did more than brighten the darkness. It gave human beings a visible rhythm between the day and the year, teaching them to count time through return. Every month on a calendar is a distant echo of people looking upward, waiting for a lost crescent to appear again. Why a day is not exactly 24 hours. The clock may insist that every day contains exactly 24 hours, but Earth has never agreed to rotate with such perfect obedience. What you call a day can refer to two different celestial measurements. A sidereal day is the time Earth takes to complete one rotation relative to distant stars, and it lasts about 23 hours, 56 minutes, and 4 seconds. Yet your daily life follows the sun rather than the stars. While Earth is rotating, it is also moving forward along its orbit around the sun. After completing one full turn relative to the distant sky, the planet has shifted roughly 1 degree around that orbit. so it must rotate a little farther before the sun returns to the same position overhead. That additional movement takes nearly 4 minutes, producing the familiar solar day of approximately 24 hours. Even this solar day is not perfectly uniform. Earth travels along a slightly elliptical orbit, moving faster when it is closer to the sun and more slowly when it is farther away. Its axis is also tilted, changing how the sun's apparent motion is projected across the sky. As a result, the interval from one true solar noon to the next varies slightly during the year. A sundial can therefore run ahead of or behind a mechanical clock by several minutes, sometimes by roughly a quarter of an hour. Civil time avoids this unevenness by using the mean solar day, an average that smooths the changing sun into 24 equal hours. Noon on your clock is therefore not always the exact moment when the sun reaches its highest point in the sky. Human timekeeping has quietly replaced the irregular rhythm of the real sun with an idealized rhythm easier for societies to share. The 24-hour day is not a fundamental unit stamped into the universe. It is a carefully averaged agreement built from a planet rotating, orbiting, tilting, and refusing to repeat its motion in perfectly equal pieces. Each midnight feels like a clean boundary. Yet beneath the numbers, Earth is continuing a far less orderly dance. How Earth's rotation is slowly changing. Earth looks like a stable clock beneath your feet, yet its hands are being nudged every day by oceans, winds, melting ice, movements deep underground, and the distant pull of the moon. The planet does not rotate as one perfectly rigid sphere. It is a layered system containing a solid crust, a slowly moving mantle, a liquid outer core, mobile oceans, and an atmosphere whose enormous currents carry mass and momentum around the globe. Whenever that mass changes position, Earth's rotation can respond through the conservation of angular momentum. The effect resembles a spinning skater extending or drawing in their arms. Moving mass farther from the axis tends to slow the rotation, while bringing it closer can make the spin slightly faster. Seasonal winds and ocean currents regularly alter the length of a day by tiny fractions of a second. El Niño events can redistribute atmospheric momentum strongly enough to lengthen a day by around a millisecond, while changes in ocean pressure, groundwater, snow, and ice can produce additional variations. Powerful earthquakes may also shift mass within the planet and alter the rotation by extremely small amounts, although these changes are usually measured in millionths of a second, rather than anything a person could feel. Deeper inside Earth, exchanges of momentum between the fluid core and the mantle can influence rotation over years or decades, across much longer periods. Tidal interaction with the moon produces a general slowing trend. Ocean tides do not point perfectly toward the moon because Earth rotates beneath them, and the resulting gravitational interaction transfers a small amount of rotational momentum from Earth into the moon's orbit. The moon gradually moves farther away while Earth's average day becomes longer. This tidal effect has increased the length of the day by roughly a few milliseconds per century on average, although short-term changes can temporarily move in the opposite direction. Scientists track the rotation using observations of distant quasars, laser ranging, satellites, and atomic clocks because navigation and astronomy require knowledge of Earth's exact orientation. The change is too small to disturb your morning, but it reveals that the ground beneath you is not keeping flawless time. Every storm system, ocean current, and shifting reservoir becomes part of a planetary clock whose rhythm is continually rewritten by the motion inside it. Why days were shorter when dinosaurs were alive? Bobai Sensei, dinosaur watching the sun cross the Cretaceous sky would have reached tomorrow sooner than you do, because Earth was spinning faster beneath it. The age of the dinosaurs lasted for more than 160 million years, so there was no single dinosaur day. But evidence shows that days were generally shorter than they are now and lengthened gradually across that immense span. One remarkable estimate comes from the fossil shell of an extinct reef-building mollusk called Torretes sanchezi, which lived about 70 million years ago near the end of the Cretaceous period. Like some modern shells, it grew in layers influenced by daily and seasonal cycles. Researchers used microscopic chemical sampling to identify tiny growth bands and found approximately 372 daily layers within one annual cycle. Earth's journey around the Sun took nearly the same amount of absolute time as it does today. But the faster spinning planet completed more rotations during that journey. Dividing the year into more days means each day had to be shorter, producing an estimated length of about 23.5 hours. The difference of roughly 30 minutes may seem modest, yet it would add an entire extra week of sunrises across 1 year. Animals would still have adapted their sleep, feeding, and activity to the local rhythm, so dinosaurs were not rushing through strangely abbreviated afternoons. Their biology developed within the faster planetary cycle, just as yours developed within the present one. Fossil shells are valuable because they preserve time without containing clocks in the human sense. Daily light, temperature, tides, and metabolism leave repeating chemical and physical marks, allowing scientists to count ancient days inside a year that ended millions of generations ago. Other geological records, including corals and tidal sediments, support the broader conclusion that Earth rotated more rapidly in the past. The main cause of the long slowdown is the continuing interaction between Earth and the Moon. But the fossils reveal the result in a more intimate way. A vanished creature once built its shell one thin layer at a time, never knowing that those layers would become a calendar for another species. You now measure 24 hours and treat that length as natural. Yet the planet remembers many older rhythms. The day surrounding you is not the day Earth has always known. It is only the current beat in a rotation that has been changing since long before anything looked up to count the sunrise. How the Moon is gradually making Earth's days longer. The Moon is quietly stealing a little of Earth's spin and carrying it farther into space. This exchange happens through tides, but not in the simple way many people imagine. The Moon's gravity pulls more strongly on the side of Earth facing it, and slightly less strongly on the far side, creating two broad tidal bulges in the oceans. Because Earth rotates faster than the Moon travels around it, these bulges are carried a little ahead of the line directly connecting the two worlds. Their gravity then pulls the Moon forward along its orbit, giving it a small amount of energy and angular momentum. As the Moon gains orbital energy, it moves outward by about a few centimeters each year, a change measured directly by firing lasers toward reflectors left on its surface by lunar missions. Earth pays for this outward motion by rotating slightly more slowly. The change is tiny on human timescales, averaging only a few milliseconds added to the length of a day over a century. And the exact rate varies because oceans, continents, ice, winds, and movements inside the planet complicate the process. Yet over hundreds of millions of years, the effect becomes substantial. Ancient Earth completed more rotations during each trip around the Sun, so the year contained more days than it does now. Far in the future, if the Earth-Moon system survives long enough without other major changes, the day will continue to lengthen as the Moon moves farther away. The process cannot continue forever in its present form, because the relationship between Earth's rotation and the Moon's orbit will gradually change, and the expanding Sun will eventually transform the system long before a perfectly stable final arrangement is guaranteed. Still, the direction of the exchange is clear. The Moon is not merely circling Earth as a passive companion. It is applying a gentle gravitational brake to the planet beneath you. Every ocean tide, every slow rise and fall along a coast, participates in a transfer that changes the duration of future days. The effect is almost impossible to feel, yet it has been shaping the rhythm of life for geological ages. The 24-hour day seems permanent only because you live inside a very short chapter of a much longer negotiation between Earth and the Moon. Why leap years are necessary. Every 4 years, the calendar appears to invent an extra day because Earth refuses to complete its orbit in a convenient whole number of rotations. A calendar year contains 365 days, but the seasonal year, the interval required for the cycle of seasons to return, is about 365 days, 5 hours, 48 minutes, and 46 seconds. That leftover fraction seems harmless, yet without correction it would accumulate. After 4 years, the calendar would be nearly 1 full day out of alignment with the seasons. After a century, the shift would approach several weeks, gradually moving summer, winter, planting seasons, and astronomical events away from their expected dates. Ancient calendar makers repeatedly confronted this problem, because neither the day nor the year was designed to divide neatly into the other. The Julian calendar attempted a simple solution by adding 1 day every 4 years, creating an average year of 365.25 days. This was a major improvement, but it added slightly too much time, because the true seasonal year is a little shorter than 365 days and 6 hours. The error was only about 11 minutes per year, yet over many centuries it caused calendar dates to drift noticeably relative to the equinoxes. The Gregorian reform introduced a more careful rule. Years divisible by 4 are usually leap years, but century years are not unless they are also divisible by 400. This is why 2000 was a leap year while 1900 was not. The revised system produces an average year extremely close to the seasonal cycle, though it is still not mathematically perfect and will accumulate a small error over very long periods. Leap day is therefore not an arbitrary tradition or a gift of extra time. It is a repair inserted into a human counting system that uses whole days to approximate an orbit containing a fraction. February receives the adjustment because of the historical development of the Roman calendar, not because that month has any special astronomical connection to the correction. The strange result is that your calendar must occasionally admit its own inaccuracy. It counts as though nature were made from clean units, then adds a day to acknowledge that the planet follows a smoother and less cooperative path. Leap years exist because the sky does not organize itself according to the numbers printed on your wall. How calendars try to control an uneven universe. A calendar is an attempt to force several celestial rhythms into one orderly system, even though those rhythms do not naturally fit together. The day comes from Earth's rotation, the month was inspired by the moon's phases, and the year follows Earth's orbit around the sun. But none of these cycles divides evenly into the others. A lunar cycle lasts roughly 29.5 days, while a seasonal year contains a little more than 12 such cycles. A year also contains a fraction beyond 365 whole days. Calendar makers must therefore choose which rhythm matters most and decide how to manage the resulting mismatch. A solar calendar keeps dates aligned with the seasons, which is useful for agriculture and civil life, but its months may lose a close connection to the moon. A lunar calendar follows the moon carefully, but its months drift through the seasons because 12 lunar cycles are shorter than a solar year. A lunisolar calendar tries to preserve both by occasionally inserting an entire additional month. These corrections reveal that calendars are not discovered in nature as complete objects. They are designed through compromise. Political power, religion, trade, and cultural identity also shape them. Rulers have renamed months, changed the starting point of the year, altered the number of days, and used calendar reform to standardize taxation, worship, and administration. Even the numbering of years depends on a chosen historical reference, not on a physical beginning universally recognized by the cosmos. Time zones add another layer of convention by dividing a rotating planet into legal regions where noon may not match the sun's highest point. International datelines decide where one named day becomes another, even though no visible boundary exists in the ocean. These systems are necessary because large societies need shared schedules, but they can create the illusion that time arrives in neat boxes. Nature is less obedient, seasons vary, lunar phases cross calendar boundaries, Earth's rotation fluctuates slightly, and astronomical cycles continue without caring whether a month has 30 or 31 days. A calendar does not control the universe in any physical sense. It controls human agreement about the universe. It tells millions of people when to meet, plant, celebrate, repay, remember, and begin again. Behind every clean page lies an uneven sky that had to be rounded, divided, and corrected. The calendar on your wall is therefore not a copy of cosmic time. It is a negotiated peace between incompatible rhythms, made convincing enough that civilization can move together. Why different cultures? Divided time in different ways. The hours on your clock may feel universal, yet much of the way you divide a day was shaped by choices made by people living under very different skies. Nature provides repeating changes, sunrise, sunset, lunar phases, seasons, but it does not label them with hours, weeks, or named years. Human societies created those divisions according to local needs, religious traditions, systems of counting, and the celestial patterns most useful to them. Ancient Egyptians divided daylight into 12 parts and darkness into another 12, partly because they tracked groups of stars that appeared in sequence during the night. These early hours were not always equal in length. A daylight hour became longer in summer and shorter in winter because the period between sunrise and sunset changed with the season. The ancient Babylonians developed powerful systems based on the number 60, a choice that influenced the later division of an hour into 60 minutes and a minute into 60 seconds. 60 was useful because it can be divided evenly by many smaller numbers, making fractions easier to handle in trade, astronomy, and calculation. Other cultures organized the day differently. Traditional Chinese timekeeping divided the full day into 12 double hours, each associated with an earthly branch, and often linked symbolically to an animal. In medieval Europe, religious communities structured daily life around canonical hours, marked by prayer, rather than by the exact numerical precision expected today. Some societies focused more on events than fixed clock units, describing a meeting as happening when cattle returned, when shadows shortened, or after a particular meal. Weeks were equally diverse. The 7-day week became widespread through a mixture of Near Eastern religion, planetary symbolism, imperial influence, and later global standardization. But other systems existed, including market cycles and weeks of different lengths. Even the beginning of a day has varied. Modern civil days usually begin at midnight, while other traditions have counted a new day from sunset, sunrise, or another meaningful boundary. These differences were not signs that one culture understood time correctly and another did not. They reveal that timekeeping is partly an agreement about which changes deserve attention. Industrial societies eventually demanded equal hours because trains, factories, communication networks, and international trade required precise coordination. Mechanical clocks helped turn time into something that could be sold, scheduled, and disciplined. Yet beneath the uniform display, older possibilities remain visible. The day can be divided by prayer, work, stars, meals, light, or numbers, and each method reflects a different relationship between human life and the world. Your clock seems to present time itself, but it actually presents one cultural solution to the problem of organizing change. The seconds feel natural only because generations before you agreed to count them in the same way. How time began. With the early universe. The earliest universe did not begin as a finished landscape waiting for events to enter it. Space, matter, radiation, and the conditions that make physical time meaningful emerged together in an extreme state, unlike anything now found around you. According to modern cosmology, the observable universe was once far hotter and denser, and it has been expanding and cooling for about 13.8 billion years. The Big Bang model does not describe matter exploding outward from one location into a pre-existing emptiness. It describes the expansion of space throughout the universe, with every observable region once compressed into a much smaller, hotter condition. When physicists trace cosmic history backward, familiar structures disappear in stages. Galaxies dissolve into diffuse gas, atoms break into free nuclei and electrons. Nuclei give way to a plasma of elementary particles, And eventually, the energies become so high that present theories can no longer describe events with confidence. The earliest interval that conventional physics can discuss is extraordinarily brief, but even there the word time must be used carefully. A clock requires a physical process that changes in a regular way, yet before atoms, stars, or stable matter existed, none of the clocks familiar to human life were available. Scientists instead describe duration through the evolution of fields, particles, temperature, density, and the expansion of space. As the universe cooled, distinct physical processes became possible, giving cosmic history more recognizable stages. Quarks combined into protons and neutrons, light elements formed, atoms eventually became stable, and much later gravity gathered matter into stars and galaxies. In this sense, the history of time is inseparable from the history of change. The early universe did not contain a giant clock announcing the first second. Its changing physical state provided the only meaning that a second could have. General relativity allows scientists to describe the expansion backward toward an apparent beginning. But near the earliest boundary, the theory predicts conditions where its own equations become incomplete. Quantum effects should dominate, and no experimentally confirmed theory yet unites quantum physics with gravity well enough to reveal exactly what occurred. This is why scientists should not claim to know that time emerged from absolute nothing at a perfectly understood first instant. The evidence strongly supports a hot, dense early universe and a long history of expansion. But the ultimate origin of time remains open. Perhaps time began with the universe. Perhaps a more fundamental quantum description existed in which ordinary duration had not yet emerged. Perhaps the earliest reality cannot be divided into moments in the way your mind expects. What you can say with confidence is that time, as measured by physical change, reaches back into a cosmos where every familiar clock disappears. You are living billions of years later, surrounded by stable rhythms. Yet every second you count belongs to a history that began when the universe first became capable of changing from one describable state into another. Why there may have been no before the Big Bang. The word before may fail at the Big Bang for the same reason that a road cannot continue north after reaching the northernmost point. In daily life, every event has something earlier than it, so your mind naturally imagines the beginning of the universe as an event surrounded by more time. Perhaps darkness waited, nothingness endured, or another cosmos existed before ours appeared. But this picture may secretly assume the very thing it is trying to explain. If time is part of the universe rather than an external container around it, then the beginning of cosmic time would not sit inside an older timeline. It would mark the boundary at which ordinary ideas such as earlier, later, duration, and cause first become applicable. General relativity connects space and time so deeply that when the universe is traced toward its earliest state, both are affected. The classical equations lead toward a singular boundary, but physicists do not interpret this simply as a known physical object called the beginning. A singularity often signals that a theory has been pushed beyond the conditions it can reliably describe. Near that boundary, densities and energies become extreme, and quantum gravity should matter. Because no complete and experimentally verified theory of quantum gravity exists, science cannot yet state whether time truly started, whether it emerged gradually, or whether the Big Bang was a transition from an earlier phase. Several serious proposals explore alternatives. Some models suggest that a previous universe contracted and then rebounded into expansion. Others describe an eternal process of cosmic inflation in which regions like ours form within a larger background. Certain quantum cosmological ideas replace a sharp beginning with a state where the distinction between space and time becomes blurred. These possibilities are not established facts. They are attempts to extend physics into a region where direct evidence is limited. Even if an earlier phase existed, it might not contain time in the ordinary sense. Asking what happened before could be like asking what sound existed before vibration, or what direction existed before space. The language assumes a framework that may not yet have formed. This creates a difficult question about causation. You normally expect every event to have a prior cause, but cause itself depends on temporal order. One condition must occur before another. If time begins at a boundary, demanding a cause that happened earlier may be logically misplaced, not because the universe appeared through magic, but because earlier is unavailable. None of this proves that there was no before. It shows why the question may have several meanings, and why honest science cannot answer it with a simple story. There may have been an earlier cosmic phase, a timeless quantum condition, or no preceding reality that can be described at all. The edge of the Big Bang is therefore not merely a distant date. It is a boundary in understanding where the grammar of human thought begins to weaken. You can follow cosmic history almost back to its opening, but the final step may require you to abandon the assumption that every beginning must be preceded by another moment waiting in the dark. How the young universe changed in its first second. Before the universe was 1 second old, it had already passed through more physical transformation than the cosmos would experience during many later ages. At the beginning of that first second, temperatures and energies were so extreme that the familiar categories of matter did not yet exist in stable form, and the earliest fraction remains beyond the reach of any experimentally confirmed theory. Cosmologists think a brief period of inflation may have occurred extraordinarily early, rapidly expanding space and leaving the universe hot, dense, and nearly uniform. But scientists still do not know what powered inflation, or whether the simplest versions describe the full story. As expansion continued, the universe cooled into a violent sea of fundamental particles. Quarks and gluons moved freely in a state called quark-gluon plasma, accompanied by electrons, neutrinos, light, and many short-lived particles that were continually created and destroyed in collisions. Particle accelerators can briefly recreate aspects of this plasma, and those experiments suggest that it behaved more like an extremely fluid liquid than a thin gas. Within the first few millionths of a second, cooling allowed quarks to become confined inside composite particles, including the protons and neutrons that would later form atomic nuclei. Matter and antimatter had also been produced in enormous quantities. When matching particles met, they annihilated into radiation, yet a tiny excess of matter somehow survived. Scientists know that such an imbalance must have existed because stars, planets, and your body are made from the remainder, but the exact mechanism that created this preference for matter is still unknown. As the first second approached its end, weak interactions became less able to keep protons and neutrons changing freely into one another, helping establish the proportions that would later influence how much hydrogen and helium formed. Neutrinos also began escaping frequent interactions with surrounding matter, leaving behind a faint cosmic population that should still fill space today. Although it has not been directly detected as individual ancient neutrinos, no atoms existed yet. No nuclei heavier than a single proton had formed in lasting abundance, and no light could travel freely through the dense charged plasma. Those developments would require minutes, hundreds of thousands of years, and eventually hundreds of millions of years. Yet by the end of the first second, many of the essential ingredients had already taken recognizable form. The universe had moved from physics we barely understand into conditions partly testable in laboratories. From freely moving quarks to protons and neutrons, and from near-perfect matter-antimatter destruction to the slight surviving excess that made every later structure possible. The first second was not simply the opening tick of a cosmic clock. It was the brief furnace in which reality decided which forms of matter would be allowed to endure, why the earliest moments of time remain hidden. The universe has preserved an ancient photograph of its childhood, but the camera could not see all the way back to its birth. The oldest light observed directly is the cosmic microwave background, released when the universe became transparent, hundreds of thousands of years after the Big Bang. Before that transition, space was filled with a hot plasma of charged particles, and light could not travel far without colliding with free electrons. Photons were repeatedly scattered, absorbed, and redirected, preventing them from carrying a clear image of earlier conditions to modern telescopes. This creates a natural wall in electromagnetic observation. No matter how large a conventional telescope becomes, it cannot simply look through the cosmic microwave background and photograph the first second using ordinary light. Scientists must reconstruct those hidden eras indirectly. The abundance of hydrogen, helium, and traces of other light elements provides evidence about the universe during its first minutes. Particle accelerators recreate tiny droplets of matter similar to conditions during the first microseconds. The large-scale distribution of galaxies preserves clues about early density patterns, while the microwave background contains marks left by processes that occurred much earlier than the radiation itself was released. Yet every step backward requires more theory and less direct access. At extremely early times, the universe reached energies far beyond those currently achievable in experiments. General relativity describes gravity successfully on large scales, and quantum physics describes particles with extraordinary precision. But the two frameworks have not yet been united in a confirmed theory capable of explaining the earliest boundary. This means scientists cannot confidently describe the first unimaginably small fraction of a second, when space-time itself may have behaved in ways no present equation fully captures. Other messengers could someday open new windows. A background of ancient neutrinos may preserve information from roughly the first second, while primordial gravitational waves could carry signals from an even earlier period. Because gravity can move through matter that traps light, neither has yet given scientists a clear, direct picture of the beginning. Researchers instead search for indirect fingerprints in cosmic structure and in the polarization of the microwave background. The absence of direct access also makes it difficult to distinguish among competing models. Several theories can produce universes that look similar by the time observable evidence begins, even though their earliest histories are very different. Hidden, however, does not mean fictional or forever unknowable. Science often learns about inaccessible events through the traces they leave behind, just as an investigator reconstructs an unseen collision from debris and motion. The earliest moments remain hidden because the universe was opaque. The relevant energies were extreme, and our physical theories become incomplete as they approach the beginning. You can follow cosmic evidence backward through galaxies, radiation, nuclei, and particles, but eventually the trail enters a darkness made not from distance, but from the limits of what nature has allowed to survive. How tiny quantum fluctuations shaped cosmic history. Every galaxy may owe its existence to microscopic uncertainty that once disturbed an almost perfectly smooth universe. In quantum physics, fields cannot remain absolutely motionless, even in their lowest energy state. They undergo tiny fluctuations, producing slight variations that would normally remain confined to extremely small scales. According to the leading inflationary picture, however, the very early universe experienced a brief period of accelerated expansion that stretched these quantum variations across astronomical distances. Differences that began far smaller than an atom could have become broad regions with slightly different densities. Inflation itself has not been directly observed, and scientists continue testing alternative models, but measurements of the cosmic microwave background strongly match several of its basic predictions. The early density variations appear nearly scale invariant, meaning fluctuations existed across a wide range of sizes with a simple pattern. They are also close to Gaussian, suggesting that most variations followed a relatively uncomplicated statistical distribution. And they are predominantly adiabatic, meaning different forms of matter and radiation were initially disturbed together rather than independently. These technical properties matter because they narrow the kinds of early universe models that can remain plausible. The microwave background reveals the fluctuations as tiny temperature differences, roughly parts in 100,000 across the sky. To the eye, that ancient radiation would appear almost perfectly uniform. Yet those faint imperfections became the seeds of everything that followed. Regions containing slightly more matter exerted slightly stronger gravity. Dark matter, which does not interact with light in the ordinary way, began gathering into an invisible network of denser knots and long filaments. Ordinary gas later fell into these gravitational wells, where it was compressed, heated, and eventually transformed into the first stars. Stars gathered into young galaxies, galaxies merged into larger systems, and clusters formed along the growing cosmic web. The process required immense time. Quantum fluctuations did not instantly become planets or living organisms, and they did not contain miniature blueprints for specific galaxies. They supplied small statistical differences, while gravity amplified those differences, and complex astrophysical processes shaped the final structures. Regions that began only slightly denser eventually became crowded with galaxies. Regions that began slightly emptier expanded into enormous cosmic voids. This creates one of the deepest connections in modern science. Quantum physics is often described as the theory of the extremely small, while cosmology studies the largest structures in existence, yet inflation may have joined the two. The uncertain behavior of fields at microscopic scales may have determined where matter would gather billions of years later. The night sky, therefore, need not be understood as a smooth universe that later became randomly decorated with stars. Its structure may be the enlarged memory of ancient quantum variation, preserved in every cluster, filament, and empty region. You exist in one small branch of that pattern, built from matter that gathered because the newborn universe was never perfectly still. Why quantum physics treats time differently from space? At the quantum level, a particle can possess no single definite position, yet the clock used to describe it is usually assumed to remain perfectly definite. This reveals one of the deepest asymmetries hidden inside standard quantum mechanics. Space is represented as something a quantum system can occupy uncertainly. An electron may be described by a range of possible positions, and a measurement can reveal one outcome from that distribution. Time, however, normally enters the theory as an external parameter that tells the quantum state when to change. The particle has a position operator that can be measured, but ordinary quantum mechanics does not provide one universally accepted time operator working in the same way. You can ask where an electron is at a chosen moment, but the theory usually does not describe the electron as being spread across several moments, exactly as it may be spread across several locations. This becomes especially strange because relativity joins space and time into space-time, placing them within one geometric structure. Quantum mechanics then appears to separate them again, treating space as part of the system and time as something supplied by a clock outside it. The familiar time-energy uncertainty relation does not fully restore the symmetry. Unlike position and momentum uncertainty, it often describes how rapidly a system changes or how long a state can remain distinguishable rather than a simple pair of equivalent measurable properties. This difference works extremely well in laboratories where researchers can rely on an external clock, but it becomes conceptually difficult when the system under study is the entire universe. There would then be no obvious clock standing outside everything else, calmly announcing when the universal quantum state should evolve. Newer proposals attempt to treat space and time more symmetrically, but no replacement has yet displaced the conventional framework that produces extraordinarily accurate predictions. Quantum theory therefore leaves you with an unusual picture. A particle may be uncertain about where it is, what energy it carries, or which path it follows, while the time used to describe those uncertainties remains quietly classical in the background. The theory can predict nature with astonishing precision, yet the clock beside its equation seems to belong to a different world from the quantum objects it measures. The mystery of whether time exists at the quantum level. If you could describe the entire universe with one complete quantum state, that description might appear frozen, containing no ordinary passage of time at all. This unsettling possibility emerges when physicists try to combine quantum mechanics with general relativity. In standard quantum theory, time is normally supplied from outside the system, allowing its state to evolve from one moment to another. General relativity offers no such external stage. Time belongs to the gravitational structure of the universe and changes with the matter and energy inside it. When these ideas are brought together in certain approaches to quantum gravity, the resulting description can lack the familiar time variable that normally drives quantum evolution. This is known as the problem of time, and it does not mean physicists have proved that nothing ever changes. It means that the two most successful frameworks in modern physics assign time incompatible roles, making it difficult to explain how the everyday sequence of events emerges from a deeper theory. One possible answer is that time is relational rather than fundamental. Imagine dividing the universe into two parts, using one changing system as a clock and describing the other relative to it. The total quantum state could remain globally stationary, while observers inside it still detect change through correlations. When the clock has one reading, the second system has one condition. When the clock has another reading, the system appears different. Page and Wouters developed a well-known version of this idea, showing how experienced evolution might arise from relationships inside an apparently timeless quantum hole. Later work has refined and experimentally explored aspects of this approach, but it remains one proposal rather than a final solution. Other approaches search for a physical variable that can act as time, allow time to emerge only in approximate large-scale conditions, or replace ordinary temporal evolution with histories and relationships between observable events. None has achieved universal acceptance. This means science cannot honestly tell you that time definitely vanishes at the smallest scale. Quantum systems demonstrably change when measured relative to laboratory clocks, and those predictions are among the most successful in science. The unresolved question is whether the clock represents a basic ingredient of reality or only an effective feature that appears when parts of the universe compare themselves with other parts. Perhaps the deepest quantum description contains moments. Perhaps it contains only correlations from which moments emerge. Time may not disappear beneath reality. It may become something that no isolated object possesses, arising only when one changing thing is used to read another. How particles can behave as though time runs backward. A particle can enter a physicist's calculation looking as though it travels from the future toward the past, even though no detector ever observes it arriving from tomorrow. This strange language became famous through the study of antimatter. In quantum field theory, every known charged particle has an antiparticle with the same mass and opposite electric charge. The antiparticle of the electron is the positron, which behaves in experiments as a real particle moving normally forward through laboratory time. Yet Richard Feynman showed that certain mathematical descriptions become remarkably elegant when a positron is interpreted as an electron traveling backward in time. In his diagrams, a line that reverses its temporal direction can represent processes such as an electron and positron annihilating or a pair being created. The interpretation does not mean a positron remembers the future, reverses aging, or can carry a message into yesterday. A Feynman diagram is primarily a tool for organizing possible interactions and calculating their probabilities, not a literal photograph of tiny objects following visible paths through time. In the laboratory, the positron is produced at one event, moves forward, interacts, and is detected later according to the same causal order as other particles. The backward time picture works because the equations connect antiparticles, negative energy solutions, charge reversal, and temporal direction in a deep mathematical relationship. It allows one object viewed under a transformed description to resemble its oppositely charged counterpart. Similar backward-looking terms can appear inside calculations of particle propagation, but they do not create a usable channel through which information can escape normal causality. The phrase also should not be confused with physically reversing a film of particle motion. Some microscopic laws possess forms of time reversal symmetry, while certain weak interaction processes reveal small but genuine violations of related symmetries. The behavior of antimatter is a more specific idea. What moves forward as an antiparticle can be represented mathematically as a particle with reversed temporal orientation. The distinction matters because sensational versions turn a powerful computational insight into false time travel. Nature has given physicists equations in which past and future directions can exchange roles more easily than human intuition permits. But the particles emerging from those equations still appear in detectors in ordinary order. They do not return to rewrite the event that created them. They merely reveal that, at the deepest level of matter, The difference between a particle and its opposite may be connected to the direction from which the mathematics chooses to read its path. Why some equations work almost equally well in reverse. If you watched two planets orbiting a star in reverse, the motion might look unusual, but the basic equations describing their paths would not immediately declare that the film was running backward. Many microscopic laws of physics are nearly time reversal symmetric, meaning that if every motion were reversed in the correct way, the equations could still describe a physically allowed sequence. A ball rising from the ground after being thrown follows the same gravitational rules as a ball falling toward it. Two particles approaching, colliding, and separating can often be mathematically reversed into particles returning along the same paths and undoing the collision. Electromagnetic and quantum equations also contain broad forms of reversibility, although reversing a process correctly may require changing more than the direction of visible motion. Velocities, magnetic effects, spins, and other properties must be transformed according to precise rules. This does not mean every reversed event is equally likely to occur in nature. The equations describe possible changes, while the initial conditions determine which sequence actually unfolds. A perfectly reversed splash would require every water molecule, air current, vibration, and fragment of energy to return with extraordinary precision. The laws may permit that arrangement, but the universe almost never prepares it. There are also genuine exceptions to time reversal symmetry. Certain interactions involving the weak nuclear force behave slightly differently when the temporal direction is reversed, and experiments with unstable particles have measured this asymmetry. These effects are real, but they are extremely subtle and do not explain why ordinary rooms never spontaneously clean themselves or why smoke does not return to a flame. The deeper lesson is that the direction visible in daily life may not be strongly written into most individual equations. It appears when huge numbers of particles begin from a particular condition and spread into overwhelmingly more probable arrangements. Physics can therefore contain rules that look almost indifferent to past and future while producing a universe whose history feels impossible to reverse. The equations may allow the road to be traveled both ways, yet reality begins the journey from only one side. How measurement gives events an order. An event becomes part of history when the universe leaves a record that another event can read. In quantum physics, a system may be described by several possible outcomes before a measurement, but measurement is not simply a human mind looking at it. It is a physical interaction in which information about the system becomes correlated with a detector, an instrument, or the surrounding environment. A photon strikes a sensor, an atom changes state, a mark appears on a screen, and that microscopic interaction is amplified until it can be stored, compared, or remembered. This amplification creates a practical order. First, the system interacts with the apparatus. Then the apparatus carries a trace of what occurred. The record cannot exist before the interaction that produced it. Quantum theory contains several interpretations of exactly what happens during measurement, and scientists do not universally agree that possibilities literally collapse at one instant. What is firmly understood is that interaction with the environment causes decoherence, rapidly dispersing quantum information across countless surrounding particles. Different possible outcomes stop interfering in an observable way, and the measuring device behaves as though one definite result has been selected. Once information has spread into the detector, laboratory, air, and memory of an observer, reversing the entire process would require controlling an impossible number of microscopic details. Measurement therefore turns a delicate quantum possibility into a durable classical record. It does not create temporal order from nothing, but it makes that order visible and difficult to erase. Before measurement, several alternatives may contribute to the mathematical description. Afterward, a result has consequences. A counter has advanced, a file has been written, or another experiment has been triggered. Those consequences distinguish an earlier condition from a later one. A sequence of measurements can then build a history with each new record depending on records already formed. This is why science can reconstruct events that no person directly witnessed. A particle track, a burst of light, or a change in a detector preserves the order of interactions. Measurement gives events an arrow, not because consciousness commands nature to choose, but because physical information is transferred, amplified, and embedded in the world. A moment becomes before when its traces are already present in what comes next. Why cause must normally come before effect? If an effect could reliably arrive before its cause, reality would lose the consistency required for prediction, communication, and even meaningful choice. A cause is not merely an event that happens earlier. It is an event whose physical influence helps produce another event. For that influence to travel, something must connect them. A force, a signal, an exchange of energy, or a chain of interactions. Relativity restricts these connections, so that usable information cannot travel faster than light. This protects causal order. Observers moving differently may disagree about which of two widely separated, unrelated events happened first, but they will agree on the order of events whenever one can physically influence the other. If a signal is sent and later received, no ordinary observer can reverse that relationship and claim the reception created the transmission. The order is built into the causal structure linking them. Quantum physics complicates the picture because entangled particles can display correlations across great distances, but these correlations cannot be controlled to send a message into the past or faster than light. Each local result appears unpredictable, and the pattern becomes visible only when ordinary information from both sides is later compared. This prevents entanglement from becoming a machine for reversing cause and effect. Some theoretical models contain unusual loops in which events could influence their own past, but such situations require extreme space-time structures and have never been observed. They also threaten logical consistency. If a message prevents the event that caused the message to be sent, the sequence seems to erase its own origin. Proposed solutions include self-consistent histories, branching outcomes, or physical mechanisms that stop causal loops from forming, but none has been experimentally confirmed. In ordinary nature, cause comes first, because effects are created through processes that take place in an ordered network of interactions. This order does not guarantee that every cause is easy to identify. Complex systems may contain feedback, hidden variables, and many contributing conditions. Yet even a feedback loop proceeds through a sequence. One state changes another, which later returns to influence the first. Causality gives the universe more than direction. It gives events responsibility for what follows. Without it, evidence could appear before the event it records. Warnings could erase the danger that produced them, and every explanation could undo itself. The future may remain uncertain, but it is protected from becoming the author of the conditions that have already made it possible. How wormholes could create loops in time. A wormhole would become a doorway into the past, not because its tunnel reversed time, but because its two entrances could be made to age by different amounts. In general relativity, a wormhole is a hypothetical shortcut connecting two separated regions of space-time. A traveler entering one mouth could, in principle, emerge from the other without crossing the ordinary distance between them. The original Einstein-Rosen bridge associated with black holes is not traversable, but later, theoretical models showed that a traversable wormhole could be mathematically described if unusual conditions held near its throat. The difficulty is that keeping such a passage open appears to require negative energy or other exotic properties that have never been shown to support a human-sized wormhole. Yet suppose an advanced civilization somehow possessed one. If one mouth remained on Earth, while the other was accelerated to a very high speed and later returned, the traveling mouth would accumulate less time than the stationary one. A similar difference could be created by holding one entrance in a much stronger gravitational field. Because the wormhole's interior might continue connecting the mouths directly, their external clocks could become separated while the tunnel still joined corresponding internal moments. You could then enter the younger mouth, emerge from the older mouth at an earlier external date, and travel normally through space back to your starting point. The complete journey would form a closed time-like curve, a path that always feels forward to the traveler, but eventually returns to an event in their own past. There may also be a strict limitation. The machine would probably allow travel only as far back as the time difference created after the wormhole was established. It would not open a route to ancient Rome or the age of dinosaurs if no entrance existed then. No wormhole has ever been observed, no method for manufacturing one is known, and quantum effects may destabilize the passage before a usable time loop can form. The concept is therefore legitimate theoretical physics, not demonstrated technology. Still, it reveals something remarkable about relativity. If space-time could be folded into the right geometry, you might reach yesterday without ever locally moving backward or exceeding the speed of light. The journey would feel ordinary at every step, while the path itself quietly curved into its own beginning. Why time travel paradoxes may prevent the past from changing. The past may protect itself not with an invisible wall, but by refusing to permit any sequence of events that contradicts the history from which the traveler came. This possibility is expressed by the self-consistency approach to time travel. If a path into the past existed, every action taken there would need to fit into the one history that already contains the traveler's departure. You might attempt to prevent a known event, yet circumstances would always produce a consistent result. The tool could fail, your information could be incomplete, or your intervention might become part of the very event you hope to stop. This idea is not merely a dramatic storytelling device. Physicists have studied simplified models involving billiard balls passing through theoretical time loops. A ball might appear destined to emerge in the past and strike its younger self away from the entrance, apparently preventing the journey that caused the collision. Yet the equations can admit self-consistent paths in which the older ball delivers only a glancing blow, changing the younger ball's direction by exactly the amount required for it to enter the loop and later produce the same collision. The past is affected, but never changed into a history incompatible with itself. Such models do not prove that the universe enforces self-consistency, and some starting conditions may allow several consistent outcomes rather than one uniquely determined history. Another possibility is more severe. The laws of nature may prevent time machines from forming at all. Stephen Hawking's chronology protection conjecture proposes that quantum effects could grow uncontrollably near the creation of a closed time loop, producing enough energy or instability to destroy the geometry before causality is violated. This remains a conjecture because physicists lack a complete theory of quantum gravity capable of settling the question. Paradoxes themselves are logical warnings, not physical forces, so they cannot directly break a machine. They reveal that at least one assumption must fail: unrestricted changes to a single past, the formation of time loops, or the belief that every apparently possible action can actually occur. The universe may allow a traveler to enter history only as someone who was always there, or it may close the entrance before history can be challenged. Either way, the past would not be a document waiting to be edited. It would be a structure whose consistency determines which journeys reality is willing to contain. The grandfather, paradox, and the problem of rewriting history. The most famous attack on time travel begins with one impossible act. You return to a year before your parent was conceived and prevent your grandfather from having children. If you succeed, your parent is never born, so you are never born, and no traveler exists to perform the act. But if you never make the journey, your grandfather survives, you eventually exist, and the journey becomes possible again. The contradiction does not come from violence or family history. It comes from requiring one event to erase the conditions responsible for that same event. Replacing the grandfather with a machine makes the structure clearer. Imagine traveling backward and destroying the laboratory before the time machine is completed. The successful destruction removes the device that carried you there, which removes the destruction, which allows the device to be built again. A single timeline cannot contain both versions as ordinary facts. Several resolutions have been proposed, but none has observational confirmation. In a self-consistent history, you may try to rewrite the past, yet you cannot succeed in a way that prevents your own departure. Your attempt was always part of the original history, perhaps causing an event you had misunderstood. A branching history model offers another answer. Changing an earlier event creates or enters a different timeline. Your grandfather could die in the new branch, while the history from which you departed remains intact, so your existence has not been erased. This avoids direct contradiction, but it does not truly rewrite your own past. It creates a separate continuation whose relationship to quantum mechanics and physical reality remains speculative. A third possibility is chronology protection, in which backwards time travel is simply impossible, and the paradox never becomes a real experiment. The grandfather paradox also exposes a difference between changing history and participating in it. You might visit the past, leave footprints, speak to someone, or cause an event. But if those actions already belong to history, nothing has been rewritten. Only your knowledge of history has changed. The paradox, therefore, does not mathematically prove that travel into the past can never occur. It proves that unrestricted alteration of one consistent timeline cannot be described without contradiction. Any workable theory would need to restrict your actions, multiply histories, or prevent the journey entirely. You may imagine the past as a room you could rearrange, but the moment your own existence depends on its furniture remaining in place, history becomes less like a room and more like the foundation beneath the person trying to move it. How closed time loops could exist in Einstein's universe? Einstein's equations permit certain universes in which traveling forward could eventually bring you back to your own past. These paths are called closed time-like curves, and they emerge when space-time is shaped so strangely that a future-directed route bends into a loop. You would never feel yourself reversing. Your watch would continue ticking normally, your thoughts would follow one another, and every step would seem to carry you ahead. Yet the geometry of the entire path could return you to an event you had already experienced. One of the most famous examples was discovered by mathematician Kurt Gödel, who found a solution to Einstein's equations describing a universe rotating as a whole. In that model, the rotation tilts the possible paths through space-time so severely that sufficiently long journeys can circle back through time. The solution was mathematically valid, but observations show that our real universe does not rotate in the required way. Other solutions involve the interior geometry of rotating black holes, rapidly moving cosmic strings, or infinitely long-spinning cylinders. Each reveals that general relativity does not automatically protect a simple division between past and future. Yet these possibilities come with severe problems. Some require infinitely large objects, unrealistically dense matter, inaccessible regions, or conditions that may collapse under quantum effects. The rotating black hole solution, for example, contains mathematical regions with closed loops, but realistic black holes are unstable and filled with dangers that may prevent those ideal paths from surviving. No closed time-like curve has ever been observed, and no experiment has shown that a traveler can return to an earlier event. Their importance lies elsewhere. They reveal that Einstein's theory is broad enough to describe geometries in which causality becomes circular rather than linear. The equations do not always distinguish a normal universe from one containing temporal loops unless additional physical conditions are imposed. This suggests that general relativity may be incomplete when pushed into such extremes, and that a deeper theory involving quantum physics may be required to decide which mathematical universes can actually exist. A closed time loop is therefore not a secret tunnel known to be hiding somewhere in space. It is a warning written into the structure of Einstein's theory. Space-time is flexible enough to imagine a road that returns to its beginning, even if nature may never allow that road to be built. Why the universe may eventually lose every useful clock. A clock can survive only while the universe contains something stable enough to repeat and enough usable energy to keep the repetition distinguishable. Every clock you have ever seen depends on organized change. A pendulum must swing, a crystal must vibrate, atoms must undergo measurable transitions, or a planet must complete an orbit. These processes require structures that persist and differences that can be detected. In the remote future, the universe may continue existing while gradually losing the physical conditions needed for useful timekeeping. As stars disappear and matter becomes increasingly isolated, there will be fewer reliable cycles available to observers. Planetary systems may be disrupted, cold remnants may drift apart, and unstable particles may eventually decay if certain unconfirmed theories are correct. Even an atomic clock requires atoms that remain intact, instruments capable of reading them, energy to operate the equipment, and a memory system that can store one result after another. A periodic process alone is not enough. A useful clock must produce records that can be compared. If no observer, detector, or durable structure remains, a billion oscillations would carry no more practical meaning than silence. The continued expansion of the universe could make this problem even deeper by separating surviving systems across enormous distances. Each isolated region might preserve a few local processes, but there would be no way to synchronize them or combine them into a broader history. Eventually, the most dependable changes might become rare particle interactions, random quantum events, or extremely slow transformations whose intervals exceed any surviving system's ability to remember them. Such events would not create an orderly calendar. They would be scattered changes without a stable framework for counting. Physics could still include a time coordinate in its equations, yet operational time, the time that can actually be measured, might fade as usable clocks disappear. This raises a quiet question. Does time remain meaningful when nothing can mark it? Scientists usually separate the existence of time from the existence of clocks, just as distance can exist without a ruler. But every scientific statement about duration ultimately depends on some physical comparison. A universe with no repeating systems, no records, and no observers might continue for an unlimited future while containing almost no way to distinguish one age from another. Time would not necessarily end. It could simply lose every instrument through which it once became visible. How the last stars will mark the final ages of cosmic time. The final natural stars may glow so slowly that a single one could outlive every star currently visible in the night sky. The universe is now in what astronomers sometimes call the stelliferous era, the age in which stars provide most of the visible light and create many of the chemical elements required for planets and life. But this era is temporary. Galaxies contain limited supplies of cold gas, and each generation of stars consumes, heats, or expels part of that material. Star formation has already declined greatly from its peak billions of years ago and is expected to continue falling. The last ordinary stars will probably be very small red dwarfs because they use their fuel with extraordinary efficiency. Unlike the Sun, which burns through its central hydrogen comparatively quickly, a red dwarf mixes much of its interior, allowing it to access a larger fraction of its available fuel. The smallest may shine for trillions of years, far longer than the universe has existed so far. They will not remain red forever. As their hydrogen is gradually exhausted, some models suggest that they may become hotter and bluer before ending as dense white dwarf remnants, without passing through the dramatic giant phase expected for stars like the Sun. After ordinary star formation ends, a few new stars might still appear through rare collisions between brown dwarfs or mergers involving stellar remnants. These late births would be isolated exceptions in a cosmos where glowing matter had become increasingly scarce. Measuring ages in that future would be unlike reading the modern sky. Today, astronomers can use clusters, stellar populations, and active galaxies as markers of cosmic history. In the distant stellar twilight, each remaining red dwarf could serve as a slow-burning clock, its gradual evolution indicating how deeply the universe had entered its final luminous era. Eventually, even those stars would exhaust their fuel. The sky would not become dark everywhere at one exact moment. Light would disappear unevenly as the last survivors faded in widely separated regions. There may be no observer present to witness the final natural star stop shining, and scientists cannot identify which object will be the last. Yet the transition has a clear meaning. Once the final long-lived stars are gone, the universe will leave the age of starlight and enter an era dominated by cold remnants and processes far slower than any human history. The last stars will not mark the end of time, but they may mark the final period in which cosmic time is illuminated, when the universe can still measure its aging through objects that burn, change, and shine. Why black holes may outlive nearly everything else. Long after the last ordinary stars have faded, black holes may remain as the darkest monuments to a universe that once burned with light. Their extraordinary longevity comes from the fact that a black hole is not powered by fuel that can simply run out. Once formed, it can persist as long as it does not lose more energy than it gains. And in the present universe, many black holes are surrounded by radiation and matter that make any loss almost irrelevant. Yet quantum physics predicts that black holes are not perfectly eternal. According to Stephen Hawking's calculation, the curved space-time around an event horizon allows a black hole to emit an extremely faint thermal glow, now known as Hawking radiation. This process slowly reduces the black hole's mass. The smaller the black hole becomes, the warmer it grows, and the faster it evaporates. But large black holes are so cold that their radiation is almost unimaginably weak. A black hole formed from a massive star could survive for vastly longer than the current age of the universe, while the supermassive black holes at galactic centers may endure for periods often estimated at around 10, followed by roughly 100 zeros in years, depending on their mass. During most of that existence, nothing dramatic would happen. The black hole would simply remain in darkness while galaxies dispersed, stellar remnants cooled, and usable matter became increasingly rare. Only in its final phase would evaporation accelerate, ending in a brief release of energy whose exact nature may depend on quantum gravity, a theory scientists do not yet possess. Black holes, therefore, are not truly immortal, but they may outlive planets, stars, galaxies, and almost every organized structure that exists today. Their endurance comes not from resisting time, but from changing so slowly that nearly all other cosmic history can finish around them. In the far future, the universe may contain little more than expanding darkness and a few remaining black holes, each quietly losing mass one almost undetectable particle at a time, until even the objects that once seemed able to imprison everything finally surrender themselves to emptiness. What time would mean in a cold and empty universe? Imagine a universe in which 1 trillion years passes and almost nothing happens that could distinguish the first year from the last. Time would not necessarily vanish from physics, but its meaning would become increasingly difficult to connect with experience. In the world around you now, duration is revealed through change. Atoms interact, objects decay, temperatures differ, signals travel, and living systems form memories. A cold and nearly empty universe would contain fewer of these contrasts. Matter might be separated by distances so great that interactions became extraordinarily rare, while the background temperature approached an extremely low value. A lone particle could continue moving, and a surviving quantum system might still evolve, so it would be inaccurate to say that time had ceased. Yet there might be no complex observer capable of dividing that evolution into days or years, and no stable environment in which records could accumulate into a history. This creates a difference between time as a coordinate in a physical description and time as something operationally measured. Physicists could imagine assigning intervals between rare events, but if no clock survived and no signal could connect distant regions, the assignment would remain local and largely abstract. Even emptiness may not be perfectly inactive. Quantum fields can possess fluctuations, and an accelerating universe may be associated with an extremely faint horizon temperature. But such effects would not resemble the rich sequence of changes that defines the present cosmos. They would be sparse disturbances in a reality approaching sameness. In that environment, asking whether 10 billion or 10 trillion years had passed might be like asking how long an unwatched, unchanging note had remained silent. The question could retain mathematical meaning while losing nearly every physical consequence. Time would continue not as a river full of events, but as an open dimension with almost nothing left to separate one region from another. The cold universe would not prove that time depends on consciousness, yet it would reveal how deeply the significance of time depends on difference. Without change, records, or beings capable of comparison, duration might remain written into the structure of reality while becoming invisible to everything inside it. Why time may end without a final moment. The universe may never reach a last second, even if every meaningful process eventually fades away. Human endings usually occur at a definite boundary. A heart stops, a light goes out, or a final page is reached. Cosmic time may have no equivalent closing event. If expansion continues indefinitely, the future could form an endless sequence in which every moment is followed by another, while the intervals between significant events grow larger and larger. Stars disappear, remnants decay, black holes evaporate, and matter becomes thinly scattered, yet no clock announces that the final permitted instant has arrived. This is an example of an asymptotic ending, a condition approached forever without being reached at one finite moment. You can understand the idea by repeatedly walking half the remaining distance toward a wall. Each step brings you closer, but the mathematical sequence contains no last step at which all remaining distance must suddenly vanish. The distant future may behave in a related way. The universe could approach complete equilibrium, near total emptiness, or another terminal condition, while always retaining some further duration in which an increasingly rare event might occur. There are other possibilities. Certain theories allow a finite cosmic ending through collapse, vacuum decay, or a destructive form of accelerating expansion, but none is currently known to be the universe's fate. If the long expansion scenario is correct, then the end of time would not mean that time is cut off. It would mean that time gradually loses its ability to produce novelty. There would be no final observer to watch the last clock stop, because the disappearance of observers and clocks would occur somewhere along the endless approach. No universal voice would say that history was complete. Events would simply become more isolated until the difference between an unimaginably long future and an eternal one mattered to almost nothing. This possibility is strangely different from death or destruction. The universe would not end by arriving at a final moment. It would end by never arriving anywhere new. Time could stretch without limit while history became effectively finished, leaving existence with an infinite future and no concluding second in which to say goodbye.